Okay, so we're moving on now to sequences and series. This chapter is a little bit different in flavor from a lot of the stuff that you've seen previously. For sequences, it's still going to remind you a lot of kind of limits at infinity like you did way back in chapter 1, right? It's going to be very similar to that. Once we get into series, the closest thing that we've seen so far that's kind of comparable to what we're doing when we deal with series is probably improper integrals, where we're not necessarily just trying to do a calculation and get an answer out at the end. We're more interested in whether something actually makes sense. So a sequence is just going to be a list of numbers. A series is going to be what you get if you add up all the numbers on a list. And by list here, we don't mean a finite list. We mean a list that goes on forever. And of course, if you're adding up infinitely many terms, then there's a good possibility that they don't add up to anything, right? They may kind of, the values might jump around and never settle down to a value. They probably add up to some infinite value if they do add up. And so it's interesting just to figure out when can we actually add these numbers up and get something sensible, right? So we're more interested in almost like existence questions now rather than computational questions. And so that gets a little bit tricky sometimes, right? It's a different philosophy than what you've been dealing with so far. But we start with sequences. We can give a definition. Okay. So there are a number of ways of defining a sequence, but the kind of definition that most people tend to give is the following. So a sequence, and I guess we should say, we could consider sequences of other numbers. We could consider sequences of complex numbers. We could even consider sequences of functions, matrices, vectors. There's lots of things that you can put into a sequence, but right now we're just looking at sequences of real numbers. Okay? So a sequence is just going to be a function. F. So I'm going to write it like this. It's a function f from the natural numbers to the real numbers. This is one way to write it. So what do I mean here? Okay, so what exactly do we mean by this notation, if you haven't seen it before? Well, what I mean is it's a function whose domain, so here n is the domain. The domain of our function will be the natural numbers, okay? So big N here stands for the natural numbers. And depending on who you ask, sometimes the natural numbers include 0, sometimes they don't. We'll allow 0 because sometimes it's convenient to have a sequence start at 0. So we're looking at 0, 1, 2, 3, 4, and so on, right? And so the idea is basically for every natural number, right, we can write those out in a list, and for every natural number on the list, we write down a corresponding real number, right? So what we're going to have is something like, say, A0, A1, A2, A3, A4, and so on. Right? So we might write it something like that. So in other words, we could say that f of a natural number is a sub n. So an here is a real number. Okay? So there's lots of things you can think of here. I mean, you can just write down any list of real numbers, and that's going to give you a sequence. Probably you want a sequence that follows some sort of pattern, right? So we might look for something like, we might have something like this. Our sequence might be something like 0, 1, 4, 9, 16, 25, and so on. And maybe by now you've guessed the pattern, right? So in other words, we can say here that f of n is just n squared. Typically, we don't really bother with function notation for sequences, so more likely how you're going to see this written, it would be simply as an is n squared, okay? So any function that you can think of, you can write down like this, and you can you can get a sequence. Here's one that's sort of an interesting one. We could do this one. AN is cosine of n times pi. So what does that give me as a sequence? Well, gives me cosine of 0, cosine of pi, cosine of 2 pi, cosine of 3 pi, and so on. But we know the value of cosine at multiples of pi. Cosine of 0 is 1, cosine of pi is minus 1, cosine of 2 pi is 1 again, cosine of 3 pi is minus 1. So you get a sequence that just alternates back and forth, 1 minus 1, 1 minus 1. Another way that you could write this, and this is typically how you would express this, would be to say, well, it's minus 1 to the n, right? Now, normally, powers of negative numbers are kind of tricky things. We don't normally like to put negatives into exponential functions. We don't like to have a negative base for an exponential because square roots, for example, of negatives don't make sense. In fact, most real number exponents, if you have a negative base, don't make any sense. Because for a real number base, right, we really, it's one thing to kind of keep in mind is to remember that, when we define a to the x, right, normally we mean e to the x times the natural log of a. So if a is negative, this doesn't make any sense, right? But we can make sense of integer powers of any number, right? Because this just means multiply minus 1 n times. So that works, right? It's n minus signs. You're just counting how many minus signs you have. And of course, if you have an even number of minus signs, you have plus 1. If you have an odd number of minus signs, you have minus 1. So you can do things like that, right? Sequences that you might have encountered in high school course would be things like arithmetic and geometric sequences where you just add the same thing every time or you multiply by the same thing every time, right? So something like, adding, just counting by twos, 0, 2, 4, 6, 8, or maybe you start at 1 and you add 5 every time, so you have 1 and 5, 1, 6, 11, 16, so on, something like that, right? These are arithmetic sequences. Multiplying by 2, like we can do, 2, 4, 8, 16, 32, 64, right? Geometric sequences, we can make sense of those. You can also look at what are called recursive sequences, and we'll encounter a few of these. And this is something that, is not a thing you can do with functions of a real variable, right? So if the domain is real numbers, this doesn't make any sense. But if your domain is the natural number, you can consider these so-called recursive definitions. So you can look at something like, maybe we define a sub 0 to be 2. And we say, okay, I'm going to define a n to be, let's say, 3 times a n minus 1 plus 1 for each n bigger than or equal to 1. And then you can kind of work out what that's going to be, right? So you start off with a 0 is equal to 2, right? A 1 will be 3 times a 0, so 3 times 2 plus 1. So I get 7, right? A 2 is going to be 3 times a 1, 7 plus 1. So I get 22. And so on. I could keep going, adding more and more terms into that sequence, generating those terms. Famous one that you might have seen is the Fibonacci sequence, right? So the Fibonacci sequence actually starts with 2 initial terms. A 0 is 1, a 1 is 1, and a n is just the sum of the 2 previous ones, n minus 1, n minus 2, for each n bigger than or equal to 2. And so you can play around and you can see what sort of terms you generate there. You get 1, 1, and then 1 plus 1 gives me 2, 1 plus 2 gives me 3, 2 plus 3 is 5, 3 plus 5 is 8, 13, 21, 34, and so on. So this is a very famous sequence. It's studied in a number of different scenarios. There's even a quarterly journal devoted just to this sequence, believe it or not. So there's lots of interesting things you can do with sequences, and there's a lot of stuff you can study with sequences, and it's kind of a gateway into studying calculus more abstractly, getting into analysis, right? The theoretical underpinnings of calculus. A lot of things can be understood in terms of sequences. Limits, in particular, can be understood in terms of sequences. We're just getting our toes wet here. We're just getting started trying to understand how things work. We spent a little bit of time on sequences, and then we're going to dive right into series. Okay, so our first example just asks us to generate the first few terms in a number of sequences written here on the board. Right? This curly bracket notation is the notation that's used in the Apex Calculus books for sequences. So we're thinking of this, if you like, as a set, I think is the idea behind the notation. Other textbooks will put round brackets around the terms in a sequence. Other books will do the, so you might find brackets around the AN. You might find no brackets at all. Notation tends to vary somewhat on these. As long as we get our point across, maybe it doesn't matter how we write it. Let's try to be consistent. Right? So with this first one, we have an exponential on top, 3 to the n. On the bottom, we have this factorial. So let me just remind you, in case you've forgotten the factorial. You probably encountered it back when you were looking at tailored polynomials, if you did study tailored polynomials along with linear approximations back in the chapter on derivative approximations. You might not have encountered them yet, depending on the order in which you see the material. Factorial is just the product of the first n integers. So it means 1 times 2 times 3, and so on up to n, right? Or another way to define it is we can define it like this. Now, one thing that's kind of odd, we do actually define 0 factorial, oddly enough. 0 factorial is defined to be 1. There are a number of ways to understand why 0 factorial should be 1 that we're not going to necessarily get into right now. One of the reasons, simple reason, is it is going to make some formulas work out a lot better for us later on once we get to tailored polynomials and Taylor series. Okay, so 0 factorial is 1. 1 factorial is also 1. And then n factorial, we just do n multiplied by n minus 1 factorial for each n bigger than or equal to 1, right? So 1 factorial is 1 times 0 factorial, still 1. 2 factorial is 2 times 1 factorial, so you get 2. 3 factorial is 3 times 2 factorial, so it's 3 times 2 times 1, you get 6, and so on, right? So with that in mind, we come over here, and 4 terms, I guess the question doesn't say whether we should start at 0 or 1. Maybe we'll start at 0 and we'll do 5 terms just to play it safe. So we'll do n is equal to 0, 1, 2, 3, and 4, okay? A sub n will be what? Will be 3 to the 0 over 0 factorial. Anything to the 0 is 1, so 3 to the 0 is 1. 0 factorial, we just said that's 1. Okay? Maybe equals is not the best thing to put here. Okay? There's A1. Sorry, A0. A1 will be 3 to the 1 over 1 factorial. So you get 3. A2 will be 3 to the 2 over 2 factorial. So that's 9 over 2. Okay. A3 will be 3 cubed over 3 factorial. Okay, so that's 3 times 3 times 3. It's 27. Sometimes it's convenient to write things out like this because you can Simplify a little bit. Cancel those 3's. It's also 9 over 2. Okay. And then 3 to the 4th over 4. We have 3 times 3 times 3 times 3. 4 times 3 times 2 times 1. We can cancel a couple of them. That's going to come out to be 27 over 8. All right. So one of the things you can see here is that initially the exponential is bigger, right? 9 is bigger than 2, 27 is bigger than 8. But each time we kind of proceed to the next step, we're multiplying on the top again by 3, but the number we're multiplying by on the bottom is getting bigger each time. So the factorial is going to grow faster than an exponential, right? And we're used to thinking of the exponential as this very fast growing thing. Factorials grow even faster, right? So eventually the denominator is going to win here, and we expect that these terms should get smaller and smaller and smaller if we let things go on long enough, okay? But there's the first 4 or 5 terms, if you like. 1, 3, 9 over 2, 9 over 2, 27 over 8. Okay. We can come to the next one. So a 0 will be 4 plus minus 1 to the 0. That's 5. Right? A 1 will be 4 plus minus 1 to the 1. So that's 4 minus 1. We get 3. A 2. Well, we're going to be back to minus 1 squared. Even power again, so we get 4 plus 1. So 5, and you can kind of see what's going to happen here, right? A 3 will be 3. A 4 will be 5, and this sequence is just going to jump back and forth between 5 and 3. So 5, 3, 5, 3, 5, 3, 5, 3 for however long you want to go. All right, let's come to this last one. You might be worried about the fraction here with the minus 1. That seems like trouble, but it's okay because, you know, whatever number n is, remember n has to be a natural number, so it's either even or odd. If n is odd, well then n plus 1 will be even. So one of these two is always even, so we divide by 2, we still get a whole number. We're fine. We can do minus 1 to an integer power. That makes sense. So, we better not start at 0 for this one, right? Can't divide by 0. So this one is definitely going to start at 1. So we'll do A1, A2, A3, A4. We do have to pay attention to these things sometimes. So A1 is going to be minus 1 to the, let's see, it'll be 1 times 2 divided by 2. Minus 1 to the 1 over 1 squared. So we just get 1. Minus 1, sorry. A2, we're going to get, let's see, it'll be 2 times 3 divided by 2. We get 3. Right? And so that's minus 1 to the 3. On the bottom we have 2 squared, 4, minus 1 over 4. A3, we're going to have 3 times 4 divided by 2. So 3 times 4 divided by 2. 12 divided by 2, minus 1 to the 6. Okay, over 3 squared, 9. So 1 over 9. And finally, A4. If n is equal to 4, we're going to have 4 times 5 divided by 2. So we have 20 divided by 2, that's 10. 10 over 2, 10, right? 20 over 2 is 10. So minus 1 to the 10, it's even again. Over 4 squared, 16, so we get 1 over 16 for that one. And again, we could keep going. Here, probably the main challenge is it seems like maybe it's a little bit hard to predict whether this thing is going to come out to be an even or an odd number as n goes on, right? The bottom we understand, that's easy to understand. Whether we should have plus 1 or minus 1 in the numerator, we'd have to think a little bit about that if we wanted to continue this sequence on any further. All right, so next up is something certainly more challenging than the previous one. So in the previous one, we were given a formula and we just had to generate the sequence. now we're given the first few terms in a sequence, and we have to come up with a formula that generates those terms. Now, one thing that's tricky here is you can't necessarily guarantee that your formula is correct, right? It might be that there are many different sequences that begin in the same way. In fact, online, there's a database of sequences, and you can go in and you can put the first few terms into that database and ask it, okay, which sequences match the terms that I'm starting? So we could go in, we could go online, we could find that website, we could enter these and see what it predicts, and maybe it only comes up with one answer, maybe it comes up with more than one. But we'll try to see if we can find one that makes sense here, right? So in the first one, we're just looking for a pattern. 2, 5, 8, 11, 14. We say, okay, what do we see about these numbers? Well, it looks to me like we're going up by 3 every time, right? 2 plus 3 is 5. 5 plus 3 is 8. 8 plus 3 is 11. 11 plus 3 is 14, right? So we can look at the differences. We see that we're going up by 3. A lot of the time what you want to do is you want to look at things like, what's the difference between terms, right? If I subtract them, do I see a pattern in the differences? Or maybe if I divide, do I see a pattern in the quotients? So you try to look for a pattern. Any way you can come up with it, you try to look for a pattern, and once you've got something that you think works, take a guess at the formula, see if your formula generates those terms, right? So in this case, we see that we start at 2 and we go up by 3 each time. So our guess is going to be that AN should be 2 plus, so each time we go up by n, we add 3. So that should just look like 3n, right? For n bigger than or equal to 0. And we guess that, and then we check. All right, so let's do 0, 1, 2. You can check the rest. I'll do the first couple. You can do the last couple. All right. N equals 0, I get 2. N is equal to 1, 2 plus 3, I get 5. N is equal to 2, I get 2 plus 6, I get 8. Looks good, right? Try the next one. If I put n equals 3, 9 plus 2 is 11, n equals 4, 12 plus 2, 14. Works. Okay? So maybe there would have been other formulas that generate those first 5 terms, but we've got one that does the job, so that works for us, right? And of course, one of the reasons why we might want to come up with a formula like this is we might want to start looking at what's the long-term behavior, right? What can we say about this pattern for large n? Does the sequence have a limit as n goes to infinity? These are problems that we want to study soon. So if we have something like this, well, we need to have a formula like that if we're going to look at things like limits, right? Okay, so we look at the next one. So one of the things that we might notice here is we're alternating signs each time, right? Plus, minus, plus, minus, plus, minus. And so one of the things that you might guess for your formula is that if you see the alternating signs, well, maybe there's a minus 1 to the n in there, right? That's something that alternates sign. So if we put that in there to deal with the minus signs, then we can focus on the numbers without necessarily looking at the minus signs. So now we have 2, 5, 10, 17, 26, 37, and we see if we can get a pattern there. All right, well, it's not as simple as the last one, but again, maybe we look at differences. 5 minus 2 is 3. 10 minus 5, 5, right? 17 minus 10, 7. So we look at the differences, and we notice the differences are 3, 5, 7, again, ignoring the minus signs. 26 minus 17, 9. 37 minus 26, 11. Those are odd numbers. Okay. So it looks like we're going up by an odd number every time, right? So we should add an odd number. Start at 2 and we add an odd number. So what does that look like? So we're going to start at 2 and we add an odd number. So an odd number looks like 2n plus 1, right? Every even number is just a multiple of 2. Adding 1 gets me to an odd number, right? And make sure that that's going to work for us. We might have to shift things a little bit. So if n is equal to 0, we get 2. Good, right? If n is equal to 1, we get a minus 1 here. That's going to be 3 plus 2, we get 5. Minus 5, yeah. If n is equal to 2, that becomes plus 1. That's going to be 5 plus 2 is 7. That doesn't quite work, does it? No, because that's just getting the odd number. So what we want to do is we want to take the previous number and add a new odd number in. So that's not quite working, is it? So it's not as simple as that. It's going to be more like, how are we going to do it? Let's see. We got to take that and we got to add the previous one. So what we're actually doing is doing something like this. Minus 1 to the n, and then we're going to do, we have that 2 at the beginning. And then we're going to do, it's going to be 3 plus 5 plus up to 2n plus 1, something like that. Well, that's not a great formula, is it? Does it work? Not really. But there's something that we might also notice. Yes, there's another thing we might notice, okay? Each of these numbers is 1 bigger than a square. Okay. Now, I noticed that because I happen to remember that there's maybe we should have noticed that right away. But there is a formula that you can prove that says if you add up the first n odd numbers, 2n plus 1, what you get is simply n squared, right? Start at 1, 1 is 1 squared. 1 plus 3 is 2 squared. 1 plus 3 plus 5 gets you to 9, which is 3 squared. 1 plus 3 plus 5 plus 9 gets you to 16, 4 squared. Right? Now, the way you actually establish that as truth is using a technique called mathematical induction. You do a proof by induction, which is not something that you're probably going to learn in your calculus course. You're going to see that maybe in an introduction to proofs course or whatever your first sort of proof-based course is. You're probably going to run into proof by induction. So what we actually want here is to realize, what we really should have is this should be minus 1 to the n, and then we should do n squared plus 1. That's going to work, right? 1 squared plus 1, 2 squared plus 1, 3 squared plus 1, 4 squared plus 1, 5 squared plus 1, 6 squared plus 1. Does the job. All right. So that one's a little bit trickier, right? This didn't work. That gave us the wrong answer, right? That's just generating the odd numbers. But those odd numbers are the differences. They're not the actual terms in the sequence. So you say, no, that didn't work. We go to this one. But that's not a very useful formula. So we find a nice closed form, and now we're happy. Okay. Getting there. Next one. Now, the next one I can spot just because I've been working with these numbers. I know these numbers. I know where they come from. So I can write down the answer right away. You might not be able to write down the answer right away, but we can start thinking about them. We'll say, okay, what's happening here? 1, 1, nothing's happening there. Then we go to 2, then 6, then 24. Okay, so what's the difference? How do these numbers compare? 2 is twice as big as 1. 6 is 3 times as big as 2. 24 is 4 times as big as 2, right? So we're doing times 1, times 2, times 3, times 4. 24 times 5 gets me to 120. 120 times 6 gets me to 720. Well, I know what these ones are. This is simply the sequence of factorials, okay? Remember we said that 0 factorial is 1, right? 1 factorial, 2, 3, 4 factorial, 5, 6 factorial. It's just the factorial sequence. Okay, not so bad. One more to go. The video is running a little long, so let's dive right in and see if we can answer this last one. We should have split this into 2 halves. 5 over 2, 5 over 2, 15 over 8. It looks okay. At first, you can't really see a pattern here, right? 2, 2, 8, 4, it drops way down, and then 32, what's going on there? Well, one of the reasons why you can't see a pattern here is that we've reduced the fractions, right? So reducing the fractions is kind of hiding what's actually going on here. 5 over 2 is the reduced form of 10 over 4. 5 over 4 is the reduced form of 20 over 16. Okay? So if we don't reduce those fractions, the numerators are going 5, 10, 15, 20, 25. Just multiples of 5. Right? And the denominators are going 2, 4, 8, 16, 32. Those are powers of 2. Okay. So on top, 5n. On the bottom, 2 to the n. And n is starting at 1. Right? Let's confirm that it works. If n is equal to 1, we get 5 over 2. If n is equal to 2, we get 10 over 4, which is 5 over 2. If n is equal to 3, 15 over 8. If n is equal to 4, 20 over 16. Works, right? We got it. All right, so in this next video, we want to introduce the idea of the limit of a sequence. So we're going to look at limits. Before we move on to examples, we need to introduce some terminology. Okay? So definition comes first. Okay? So we say that a sequence an, and the term that we use here is converge, okay? Just like for improper integrals. So we're going to say that the sequence converges to a limit L, okay? And we might just say the limit is L. And so we write this as limit n going to infinity. So we only look at limits at infinity for sequences. The limit of an is equal to L. If, all right, we're going to give the precise definition. If for any positive epsilon, there exists a natural number n such that for all n bigger than or equal to that n, the difference between an and L is less than epsilon. Okay? All right, so the definition is a bit of a mouthful. Okay? So the key word here is converge, right? Or limit, if you like. Here's our standard notation. Okay? Limit of the sequence is L. So we get into this epsilon delta formulation again, right? For epsilon greater than 0, there exists an n such that for every little n that's bigger than this fixed n, right? So here, think of this as the variable, this is some number. We have this inequality. Visually, this sort of makes sense. Okay, so what we're really saying here when we say we have a limit, think about things graphically, right? We can plot the terms in a sequence because we can remember that we can think of a sequence as just a real valued, or it's a real valued function where the domain is just the natural numbers. Right? So we can mark our natural numbers down. And we have some value, say L. So L is going to be the limit, let's say. All right, so let me just draw that line in. Y is equal to L, okay? And epsilon here, think of epsilon as like an error, right? What we're saying is that the difference between terms in the sequence and the limit will be small. Okay? So what we're saying is that for any epsilon, so we can choose a large epsilon, but typically we think of that as a small epsilon. So here's L plus epsilon. Here's L minus epsilon, right? So we get this little strip of with 2 epsilon centered on L. And then you stop plotting the terms in your sequence, right? And so maybe the first one is down here, like here's A1, right? And maybe A2 is up here. And maybe A3 is down here. And A4, maybe it's up there. Okay, A5 is here. A6 is there. A7 lands inside. Oh, great. But then suddenly A8 is out again. Okay, but then A9 is inside. A10 is inside. 11 is inside. 12 is inside. All right. So there's some value of n right here, right? So that once we hit there, all the later terms in the sequence are going to be within that strip. And of course, this is saying that the terms in the sequence, they do have to get closer and closer and closer to L. Because if I shrink the strip, right, if I make epsilon smaller, if I make this narrower, well, then I might have to go further out before I find an n that works. But we're saying, if we say that we have a limit of L, we're saying that no matter how thin I make this strip, I can eventually go far enough out so that everything stays inside the strip, right? Thinner strip, bigger n, but I can always do it, right? Eventually I'll always get inside the strip. So that's what it means to have a limit in this sense. All right, so in the last video we introduced the notion of convergence of a sequence, right? So this is just whether or not the limit of a sequence exists and gives a finite value as n goes to infinity, right? So if you calculate the limit and the limit is either infinite or the limit doesn't exist, then we would say the sequence diverges. So a convergent sequence is going to be one where we actually get a number for the limit. So that's what we're looking for here, okay? Now, one of the things that is worth pointing out is that if your sequence is, given by f of n, where we know how to do this limit, the limit as x goes to infinity. So if we replace n with a real variable, x, and we calculate that limit and it exists, well, then the limit as n goes to infinity of an will agree, right? Now, that doesn't always work because there will be situations where this limit doesn't exist, but we can still make sense of the sequence, because there might be functions that, for a real variable, they're jumping around all over the place, but you put in only integer values and things settle down. But this does give a handy tool, especially for something like this, because we know how to do a limit like this, right? We know that if we were doing the limit as n goes to infinity of 3n squared minus 2n plus 1 over n squared minus 1,000, right? If we had x instead of n here, then this is a problem that you did way back in the very first chapter on limits, right? Very beginning of Calc 1. We'd say, okay, it's quadratic top and bottom, right? If the degree is the same on top and bottom, we look at the ratio of the coefficients, 3 over 1. We know that limit is 3. So it converges. It converges to 3. So that's simple enough, right? It's good enough to do that. I mean, you should say something, right? Say, why is it 3? Well, because it's the same degree top and bottom, and that's a rule that we learned, right? If you feel like that's too easy and you want to show a little bit of work, well, you could always do that same trick that we did with the real variable, divide everything by n squared, right? So you could write this as the limit n going to infinity of 3 minus 2 over n plus 1 over n squared, 1 minus 1,000 over n squared. And you can use the limit definition. You can give an epsilon n proof to show that the limit of anything, any constant over n, that limit is going to be 0. Same with n squared, n cubed. You know, constant over any positive power of n is going to go to 0. So we get 3 over 1 in the limit, we get 3. Great. You move on to something like this. Well, this, if you plot it, it's an interesting thing, because if you plot this function, if you plot the sequence, right? I mean, we know what it is, a function of x, so you get this cosine wave. It oscillates back and forth. But if you start plotting the points for this sequence, the textbook has this scatter plot, shows you what it looks like. Well, then it's a little bit different, right? Because you're only plugging in the integer values. So you're getting points that are on that cosine wave, right? But only at the integer values. And the cosine wave, you know, if we're just doing cos n, it's not oscillating with an integer period, right? The period is a multiple of pi. So things are going to actually jump around a whole lot. It's going to be kind of funny looking. But nonetheless, we know for sure that this is not going to exist, right? So this limit diverges. So this sequence diverges. I mean, we need to give a reason for it. But one of the things we know is that, well, we know the limit as x goes to infinity of cos x. That doesn't exist, right? Because it oscillates back and forth between -1 and 1, right? We hit those values infinitely many times. Now, we're not actually going to hit -1 or 1 for this, because we're not actually going to get to, you know, a multiple of pi over, to a multiple of pi, right? We don't get to a multiple of pi. But we get close, right? So somewhere along the way, you know, n's going to infinity, we have all the integers in there. So somewhere along the way, we have you know, 3, all right? We have 31, 314, right? 3,100, you know, 41. We have 3,100, or 31,415, you know. We have these numbers which are very close to multiples of pi, right? We can kind of add more digits of pi, but before the decimal, right? So this is close to 100 pi, 1,000 pi, 10,000 pi, right? Those are all even multiples of pi. And then we could also consider, you know, odd multiples. We can shift things a bit. So we can get lots of values that are close to 1. We can also generate values that are close to -1. We can get all kinds of things in between, right? So it's never going to get close to any value. It's going to keep jumping back and forth forever. So that's no good. Okay. Now, you come to this last one, and there are a couple of ways that you can tackle something like that. One would be to go to the definition, or I mean, you want to probably play around a little bit, right? And you say, okay, well, the terms in the sequence are going to be, I'm going to have like -1, then I'm going to have a half, then -1/3, plus a quarter, -1/5, plus 1/6, right? And so if you start plotting them, you can kind of see that, yeah, it looks like they're going to 0, because you have, well, one way to think about it is that you have, if we draw in, here's y is 1 over x, and down here we can put in y is -1 over x, right? And so the terms in the sequence are going to be, you know, I guess the first one would be down here, and then up here, and then here, and then there, and then there, and then there, right? So you can see that they're getting closer and closer to 0. The trouble is we can't write this as a function of x as it is. -1 to the x makes no sense. At least if we're working with real numbers, it makes no sense. Now, one of the things you can do is something that we observed initially. Here is a function that actually agrees with this sequence on the integers. Cos pi x over x, right? Because multiples of pi, right, integer multiples of pi, you plug them into cosine, you get either 1 or -1, like we were just talking about. So there's a function of x that agrees with our sequence at every integer, and if you take the limit of that, well, we saw that again, but go back to Calc 1 methods. Squeeze theorem essentially is going to tell you, right? Because the absolute value of this f of x, right? Well, absolute value of cosine is less than or equal to 1. So this is less than or equal to 1 over x in absolute value. And so the function is sandwiched in between minus 1 over x on the one hand and plus 1 over x on the other hand. We know that those both go to 0, so this has to go to 0 as well. Actually, that squeeze theorem argument, you can use that for sequences as well. That's perfectly valid, right? We can just say, well, look, it's true that minus 1 over n is less than or equal to cn, less than or equal to 1 over n for all n. And we know that that goes to 0. We know that that goes to 0. Squeeze theorem says that this has to go to 0 as well. So we know that the limit as n goes to infinity of cn is 0. So it converges, and it converges to 0. All right, so here are a couple of theoretical results on limits that can come in handy. The first one we just actually employed towards the end of the last problem, the last example, where we noted, we had this, remember what the problem was. We were trying to do the following limit, right? We said, okay, we have this limit, n goes to infinity, of minus 1 to the n over n. And we said, well, you know what? We'd sure like to just sort of argue that since minus 1 to the n just goes back and forth between minus 1 and 1, it's bounded. N is going to infinity, so this is a number that's always either 1 or minus 1, dividing by larger and larger numbers, that things are getting closer and closer to 0. We found a couple ways to kind of argue that, yes, that limit does indeed have to go to 0, but here is one theorem that kind of lets you do it quite quickly, right? If a sequence goes to 0 in absolute value, then the sequence has to go to 0. And it is exactly that same sort of squeeze theorem type argument that we gave towards the end of that solution. We said, okay, well, this just works because any number is either equal to its absolute value or the negative of its absolute value, right? So it's in between those two. And so if this goes to 0 in the limit and that goes to 0 in the limit, well, then this one in the middle has to go to 0 as well, right? Or if you like, you could use the definition, right? You could go back to that epsilon n definition and you say, okay, we let epsilon be given, and we can say that since the limit as n goes to infinity of the absolute value of n is 0, we can choose n such that the absolute value of an minus 0 is less than epsilon, right? But then, just think what this is. Well, I mean, minus 0, this is just, so it's the absolute value of the absolute value. But that's just the absolute value of an, right? Which is the absolute value of an minus 0, right? So that same n is going to work here because really the absolute value of an is the same as the absolute value of the absolute value of an, right? So just get it right away with really no effort. Limit properties work the same for sequences as they do for functions, right? If you have two convergent sequences with finite limits, right, then the limit of the sum is going to be the sum of the limits. If there's a constant, you can pull it outside the limit, right? So you can think of this is just k times the limit of an, right? Limit of a product is product of the limits. Limit of a quotient is the quotient of the limits. Well, as long as the limit of Bn is not 0, right? So you can do all of these things. We won't necessarily go through the proofs in a calculus class. Again, you might see them in another course, maybe in an analysis course, probably just in a basic intro to proofs course, you're going to see something like that. The proof for the limit of a sum is a standard one that you're probably going to encounter, and it's a sort of nice one to see. go through the details. I don't know if we want to do it here. We only have so much board space. We don't want to make the video too long. I'll just kind of explain the idea of the proof for the limit of a sum, right? So for the limit of a sum, right, you're given, so epsilon is given, right, and you're trying to make this difference smaller than epsilon, right? But I can rewrite this as an minus L bn minus m, just rearrange things, okay? And if you were doing, and by the way, if you're doing the difference, you'd have a minus sign here instead of a plus sign, and the next step actually is the same. You have the triangle inequality. The absolute value of a sum is always less than or equal to the sum of the absolute values. All right, so you can get something like that. And so I'm not going to write up all the details of the proof, obviously, I don't have room, but essentially the way you would proceed is you'd say, okay, I'm given the epsilon, now I got to choose my n. And you say, okay, well, look, I know that this limit exists, right? That limit is L, right? So an converges to L. So I know that from here I can choose some n1 that makes this absolute value less than epsilon. I can choose an n2 that makes this difference less than epsilon, right? Because I know that those two sequences converge. And then what I do is I choose n to be whichever of those is bigger. n1, n2, right? So that means that if little n is bigger than big N, well then it's bigger than both of these. And so I know that that difference is less than epsilon, and I know that that difference is less than epsilon. Except, then the sum is going to be 2 epsilon, and that's not quite what we want. So we say, hey, actually we can choose these so that this will be less than not just epsilon, but that'll be less than epsilon over 2. And we choose, so this is less than epsilon over 2. And so then when we add them together, we get that epsilon, right? That's a standard kind of argument that you use for doing epsilon delta proofs with sums or differences. All right. So in this example, we're going to work with some of the limit properties for limits of sequences that we saw in the previous video. We're given 3 sequences. We're told their limits, okay? Some of these, we can work these out if we absolutely had to, but they're given to us, right? Here, if we wrote all of these as functions of x, and we think about taking the limit as x goes to infinity, we know how to handle this. It's just a rational function. Degree is bigger on the bottom, so yes, the limit should be 0. This one here, this is interesting, right? That is like base e from like the natural exponential function, right? That's Euler's number. Some people will actually take this as the definition of e, which is interesting, but you can show that the limit is equal to e using L'Hopital's rule, right? Techniques for indeterminate forms, because this is something of the form 1 to the infinity. That's one of the forms that we know how to handle. Finally here, this one's a little bit tricky. If you try to take the limit, well, let's see, n's going to infinity, 5 over n's going to 0, so it's like infinity times 0. But if we wrote this as sine 5 over n, if we think of this as sine 5 over n divided by 1 over n, now it's a 0 over 0 limit. And in fact, if we put a 5 here and a 5 here, well, now this is like a sine theta over theta limit, right? We know that limit as, if n goes to infinity, 5 over n goes to 0. So we know that this limit here is 1. So 5 times 1, so that makes sense. Okay, so we have these limits. Now we want to calculate these results over here. And the point is, once we know the value of the limits, we don't need to get into the details. We just need to apply limit properties. So this one here, well, we know that the limit of a sum is the sum of the limits. So we can write limit as n goes to infinity of an plus the limit as n goes to infinity of bn. And The first limit is 0, the second limit is e, and so the result is going to be e, right? Similarly here, we have a product. Limit of a product is product of the limits. As long as these two limits exist independently, right? We can have situations where this limit does exist, but these limits don't, and then you got to be a bit more careful. So we can do that. Okay, and limit of bn is e, limit of cn is 5. So e times 5, or maybe we would prefer to write that as 5e. Okay, and the last one, we have a constant multiple. So if you have a constant multiple, you can bring it outside the limit. So this is 1,000 times the limit as n goes to infinity of an. So it's 1,000 times 0, which is 0, right? So it's not so bad. So the next thing that we're going to look at is what it means for a sequence to be bounded. Okay, so here's a definition. Okay, so we'll have a sequence, let's say an. And we'll say that it's bounded if, it's underline bounded, so it's bounded if there are constants, let's say little m and big M, such that an, each term in the sequence an, is always between little m and big M. So little m is your lower bound, big M is your upper bound, and of course we need that to hold for all natural numbers, right? It's for all n equal to 1, 2, 3, and so on. We require every single term in the sequence to be between these two bounds. Okay, so that's a relatively straightforward definition. Visually, you can sort of think about how this looks, right? If you plot the terms in your sequence, you have some upper bound big M, some lower bound little m, and every term in the sequence has to lie in between those two bounds. Okay. So we come over here to this example. We've got a couple of sequences. We want to decide whether or not these are bounded. It becomes pretty clear once you start writing out terms in the sequence, right? So here we have 1, 1/2, 1/3, 1/4, and so on. So in particular, they keep getting smaller, right? And I think it's pretty clear here that we have 1/n less than or equal to 1 for all n bigger than or equal to 1. In fact, if you just take reciprocal of both sides, right? If you have an inequality involving positive numbers and you take reciprocals, the inequality reverses and done. Okay. On the other hand, if we come over to here, you look at the sequences, right? 2, I mean, maybe we start at 2 to the 0, so 1, 2, 4, 8, 16, so on. These are not going to be bounded, right? They grow without bound. It's an exponential function. We know, in fact, we know that the limit as n goes to infinity of 2 to the n is infinite, so they can't possibly be an upper bound, right? These numbers grow without bound. All right, so in this video we're going to discuss a theorem related to bounded sequences. The theorem says that every convergent sequence is bounded. So in other words, if the limit as n goes to infinity of an is equal to L, and L is some finite value, right? L is less than infinity, then the sequence AN is bounded, right? That's what it says. Now, be careful. This does not say that every bounded sequence is convergent. It says every convergent sequence is bounded. So you got to be careful. Those are two different statements. One is true, one is false. This one is true, and let me show you why. We'll actually prove this. So let's suppose that the limit as n goes to infinity of an is equal to L, okay? Now, let's think about the definition of convergence, right? Definition says for every epsilon, I can choose a capital N so that for every little n bigger than that capital N, the difference between an and L will be less than epsilon. So I can choose any epsilon because I know this limit exists. So if I take epsilon equal to 1, there has to be some capital N such that the absolute value of an minus L is less than 1 for all n bigger than or equal to big N. Now, another way to rewrite this is to say, well, that means that this difference is between minus 1 and 1. And if I add L to everything, that means that minus 1 plus L is less than an is less than 1 plus L, right? So an is between L plus 1 and L minus 1, okay? But only for those values of n that are bigger than or equal to this capital N, right? What about the ones that came before? Well, the ones that came before are a finite list, right? So basically what we do is we're going to let big M be the maximum of all the numbers A1, A2, A3, and so on, down to let's say n. Maybe you want to go n minus 1 if you want, but it's fine, let's leave it in. And also, we throw in L plus 1. And we can let little m be the minimum of A1, A2, A3, down to AN, and then L minus 1, right? And so essentially that's it. If we take, any term in the sequence, any an in the sequence, well, then it has to be less than or equal to the biggest of these numbers. If it's, so if it's one of those terms, it has to be less than or equal to one of these, right? Whichever one of those is biggest. And if we take an an for little n bigger than this capital N, well, then we know that an has to be smaller than L plus 1, right? So whichever one of these numbers is biggest, that's the upper bound. Similarly, whichever one of these numbers is smallest is going to be the lower bound. So we know that an has to be in between for each value of n, and that proves the theorem. Okay, so every convergent sequence has a bound. We've just demonstrated it. But not every bounded sequence converges, right? A good example of that is you just take like the sequence minus 1 to the n. It's bounded, right? It's always between minus 1 and 1, but it goes back and forth forever. It never settles down to a limit. So there are bounded sequences that don't converge. We can add one more condition that does guarantee convergence, and that's what we're going to talk about in the next video. So the next thing that we want to talk about is monotone sequences. So this is a definition. Has two parts. So part 1, part 2. Okay. a sequence AN is monotone increasing if AN is less than or equal to AN plus 1 for all natural numbers n. And similarly, it's decreasing if AN is bigger than or equal to AN plus 1 for all natural numbers n, right? So it's a very simple concept. It aligns fairly well with what we understand for increasing, decreasing functions. Although we do allow, we don't insist on a strict inequality here. We allow less than or equal when we're dealing with sequences. So monotone increasing, monotone decreasing, right? This condition here just says that the next term in the sequence has to be at least as big as the previous term, right? Here, the next term in the sequence is less than or equal, so these ones are getting smaller, these ones are getting bigger. Simple enough, right? So there's an important theorem. Related to monotone sequences, bounded monotone sequences, which says, and collectively we can say monotone if it's either monotone increasing or monotone decreasing. And the theorem says the following. The theorem says every bounded monotone sequence converges. Okay? So that's what the theorem states. So we mentioned before this previous theorem, we proved that every convergent sequence has to be bounded, and I warned that the converse is not true, right? Every bounded sequence is not necessarily convergent. But if we do have a bounded monotone sequence, right, the added condition of monotonicity guarantees that you can't have this sequence that's jumping back and forth, right? Because it always has to be going up or always going down, okay? And so you're guaranteed convergence for every bounded monotone sequence. We're not going to prove this theorem because a proof requires actually getting into careful sort of axiomatic definition of the real numbers. You have to talk about least upper bounds, least upper bound property of the real numbers. But intuitively, it's pretty clear why this has to work, right? So if we think about a bounded monotone increasing sequence, right? So if it's increasing and bounded above, right? If that's our upper bound and our sequence is increasing, so maybe we start here, we go up, it's increasing, right? But we can't pass n, right? So each term has to get bigger, but we can't get any bigger than m. Right? We can't go back down because then we wouldn't be monotone increasing. We can't cross m because it's an upper bound, right? And so the idea here is the way you would prove this is one of the properties that the real numbers have is that any sequence that is bounded above has a least upper bound. And so basically you would say, well, look, here's a sequence of numbers. It's bounded above. We look for the least upper bound, and you can prove that that least upper bound has to be the limit, right? But then you got to get into this discussion of least upper bound properties. And of course, for a sequence which is monotone decreasing and bounded below, well, it's going to do the same sort of thing, right? It's going to decrease down until we get closer and closer to that lower bound, but we can't pass it, so we approach whatever the greatest lower bound is, and that's going to be the limit. All right, so here are four sequences. We want to decide if these are monotone increasing, monotone decreasing, because we're interested in whether we can apply this theorem we've just discussed, right? We have a theorem that says that every bounded monotone sequence converges. And so if we can identify when a sequence is bounded and monotone, well, then we have a very powerful tool for determining convergence of a sequence. So let's look at these. The first one's pretty straightforward. We might notice that n plus 1 over n can be written as 1 plus 1 over n. And it's also pretty clear that this is going to be decreasing, right? Because as n gets bigger, 1 over n gets smaller. And so this is going to be decreasing. Well, maybe that's not a very watertight argument. You know, it's essentially appealing to the fact that these terms lie on the graph y is 1 over x. We know that that's decreasing, so we go with it, right? Now, there's a couple of ways that you could actually establish this, right? So one way you could establish this is we could say, well, you know, if I let f of x equal 1 plus 1 over n, or I guess it should be x now, sorry, right? So our sequence is just the values of f of x when we restrict the domain to the natural numbers. But we know that the derivative of this thing is minus 1 over x squared, which is less than 0 if x is bigger than 1, bigger than or equal to 1. And it's less than 0 for every x, but in particular for x less than or equal to 1. And so that certainly establishes that this is a decreasing sequence. The other way you can do it is you can consider the difference, an plus 1 minus an. Okay? If our sequence is decreasing, then this term should be smaller than that term, so this difference should be negative. So we can try to show that that difference is negative. You can go ahead and try it, but we'll do it in the next one, right? It is done in the book. If you want to look in the book, you can go through how to do it that way. We'll apply it in the next one because we've got 4 examples to get through, and we don't want this video to get too long. Okay, so how about the next one? We could once again kind of use this function argument here, but we could just go ahead and do it, right? So this time there's not a nice simplification, but we can say, well, what do we get if we do b n plus 1 minus bn? Okay, what does that look like? Well, we're going to have n plus 1 squared over n plus 2 subtract n squared over n plus 1. And we'd like to get a common denominator for that. So we're going to get n plus 1 cubed minus n squared times n plus 2 over n plus 1, n plus 2. And, well, now we've got to multiply this all out. N cubed plus 3n squared plus 3n plus 1, using binomial theorem, minus n cubed minus 2n squared over n plus 1, n plus 2. And so we take a look at this and we say, all right, that cancels with that. 2n squared, that cancels with 2 of those. 3 leaves you with 1. And, okay, so we have n squared plus 3n plus 1, n plus 1, n plus 2. That's positive, okay, because n is positive. And so now we know that this particular sequence here is increasing, right? Because the difference is positive. Good. One decreasing, one increasing. We can go to the next one. So the next one actually, you know, it's going to bounce around on you initially, you might find, if you start plotting some of the values. Textbook does that for you. Right, we can consider, you know, if n is equal to 0, what do we get, right? If we sort of start writing out the terms in the sequence, when n is equal to 0, we have minus 9 over 26. When n is equal to 1, we have minus 8 over, what are we going to get? 17, right? N is equal to 2. We have minus 5 over 2. Right? N is equal to 0. We get 0, right? And so on. We can start plotting these and sort of play around and see where they go. And it's kind of hard to tell looking at those values to figure it out. We can do this sort of difference method again. The textbook does that for you. It's a big mess, though. You might want to sort of analyze the two polynomials in n that you see here, see if you can get anything out of that. You might want to, for example, well, the top we can factor. I don't know if that helps us at all, but we can factor it. The bottom, let's see, the bottom we could complete the square, n minus 5 squared plus 1. Well, it's never 0, that's good news. You can play around with that. You can do this difference, but it's going to be ugly. So maybe we do want to look at this one from the point of view of a function. We say, okay, let's consider f of x to be x squared minus 9, or x squared minus 10x plus 26. What's the derivative? F prime is going to be 2x times x squared minus 10x plus 26. Good old quotient rule. Okay. Subtract x squared minus 9 times 2x minus 10. Whole thing over x squared minus 10x plus 26 all squared. Okay, let me clean that up, give myself a bit more room. F prime of x, so I've got 2x cubed minus 20x squared plus 52x minus 2x cubed from here. And then I've got minus 10x squared minus plus 10x squared. Minus 18x plus becomes plus 18x. And then minus 90. Well, that's a mess. But you know what? It's actually okay. It's not as bad of a mess as you might think. We look for cancellations again. We can cancel there. We can cancel there. This is with 10. That adds up. So we get, and then that's going to be 70, right? So we get on top. Now, the bottom is never 0, right? We established that up here. This numerator is always positive, and we're squaring it. Yeah, so I mean, we just got to focus on the numerator. So that numerator, we've got minus 10x squared plus 70x, okay, minus 90. Okay, so this is a quadratic and it's opening downwards, right? We can, in fact, we can pull out the minus 10. So we have x squared minus 7x plus 9. Okay. And it doesn't factor super nice, but we can definitely tell that it's a quadratic, it's opening downwards. So these terms are initially increasing, right? They're initially increasing towards sort of that vertex in this quadratic on, you know. So there's a few values of n at the beginning where we're on this side of the quadratic and things are increasing. Once we hit that maximum, it's going to be decreasing, right? So we expect that this is an eventually decreasing sequence. It's not decreasing from the beginning, it's increasing a bit at the start, but it's eventually going to start decreasing, which is good enough. Okay, we're getting a little long here. There's one more still to go. What can we say about this last one? The factorial we can't really model with functions anymore. We could try looking at the difference. This might be one where it makes sense to just start writing out terms. And initially it seems like it's increasing, right? So we have 1 for n equals 1. And then we're going to have 4 over 2, so we have 2. And then we have 9 over 6. Oh, that's already actually a little bit smaller, right? 16 over 24, right? And then we have 25 over 120, and so on. This is definitely decreasing, right? The factorial is going to grow much faster than the power function is. So you have a decreasing sequence. If you wanted to really kind of nail it down, you could kind of look at this sort of difference again. You could say, okay, what does the difference look like? N plus 1 minus dn. So you have n plus 1 squared over n plus 1 factorial minus n squared over n factorial. Actually, if you remember that n plus 1 factorial is n plus 1 times n factorial, right? It's defined recursively. Then what you have here is just n plus 1 over n factorial minus n squared over n factorial. Okay? And so it's minus n squared plus n plus 1 over n factorial. That is definitely going to be negative for large values of n, right? So once we pass here, it's definitely negative. We have a decreasing sequence. All right, so we're pretty much done with sequences now. Ready to move on to series. Before we do, I want to show you one more, let's say, slightly more challenging example. This one has a sequence which is defined recursively, right? So we don't have a formula like most of the ones we've been dealing with so far. We just have some formula that says an is this function of n, right? And a lot of the time we can fall back on calculus techniques that we already have to understand what's going on. But this one is defined recursively, so we don't have a function that we can work with. So how do we find the limit of such a thing, right? I mean, you can start thinking about like what do the terms look like? You know, a1 is root 2. a2 is root 2 plus root 2. a3 is root 2 plus root 2 plus root 2, and so on. Is that even going anywhere? If so, where? Right? It's not at all clear. How do we figure this out? Well, we know that bounded monotone sequences converge. Okay? So one of the things that we can do is we start plugging values in, put them in the calculator, you see what you get some numbers out, right? By the time you get to like A4, it's starting getting complicated enough that maybe you don't want to put it into the calculator anymore. But you can try a few. And if you try a few, you find that you're getting numbers that are 1 point something, they seem to be hovering a little bit below 2. So you might guess that 2 is an upper bound. So that would be the first claim. So we're going to claim that an is less than or equal to 2 for all values of n. Well, how do you show that? How do you show that an is going to be less than or equal to 2 for all values of n? It's a little tricky, right? How do you deal with this recursively defined thing? You could look at the difference, 2 minus an. Can we do anything with that? Let's see. I mean, 2 minus an is, well, what can I even say about an? I don't know. I can say it's like, well, I'm sorry. 2 should go on the inside. Put the square root of an minus 1. Does that get me anywhere? I want to show that this is positive, right? I want to show that this is less than 2. So I want to show that 2 minus an is bigger than 0. Not at all clear. I could try rationalizing. Does rationalize get me anywhere? We are going to go somewhere, don't worry, right? We get 2 minus there. And then we get, 2 plus that square root on the bottom. And okay, you can simplify. Those cancel. That's a plus. But you still feel like maybe you're stalled. So how do you proceed? Well, the right way to do this is you proceed using a technique called induction. So we're going to proceed by induction, okay? So induction on n. So the way this looks is we say, okay, so first of all, we know that A1 is less than 2, right? Because A1 is the square root of 2, we know that the square root of 2 is less than 2. Okay? 2, we're going to suppose we know that some AK is less than or equal to 2. Right? Actually, we do. We know what when k is equal to 1, right? And so what we're going to do is we're going to imagine, well, maybe we also know this for some other values of k, 2, 3, 4. We don't yet, but suppose we did. So the next step is we say, well, if we know that, can we show that ak plus 1 is less than or equal to 2? This is how an induction argument works. Now, we're going to do it. Before we do it, let's point out why it works. Why does this work? Well, essentially, what you're showing here is you're showing this implication, right? You're showing that if this is less than or equal to 2, then the next one will be less than or equal to 2. So we have this implication going like that. We know A1 is less than or equal to 2. So this is true when k is equal to 1. But if the hypothesis of a conditional is true, so is the conclusion. So we know that A1 is less than or equal to 2, therefore A2 is less than or equal to 2. But now we come back, right? A2 is less than or equal to 2, therefore A3 is less than or equal to 2. Since A3 is less than or equal to 2, A4 is less than or equal to 2, and so on. So we just kind of get into this loop and we generate all the other possibilities. So it remains to show that if AK is less than or equal to 2, then AK plus 1 should be less than or equal to 2. Well, why is that true? If we assume AK is less than or equal to 2, well, then we get that AK plus 1 is, well, by definition, it's 2 plus square root of 2 plus AK, right? Oh, but we've assumed that AK is less than or equal to 2. So this must be less than or equal to the square root of 2 plus 2, right? Replace AK by something bigger. But 2 plus 2 is 4. Square root of 4 is 2. Okay? And that means that AN is less than or equal to 2 for all natural numbers n using this technique of induction. Very good. Okay. So now we want to show that, so we've shown it's bounded, now we want to show that it's monotone. Okay? So I'm going to claim that AN is less than or equal to AN plus 1 for all n. I want to show that it's increasing. Okay? And so we could try something like this. We could try playing around with differences, and I think you can sort of get something to work doing it that way. You can look at the difference. You can put in the definition. I mean, let's check quickly and see what happens. If I do the difference, AN plus 1 minus AN, well, that's root 2 plus AN minus AN. Rationalize, I get, it's going to be 2 plus AN. oh, well, you know, this isn't so great either, right? Because if I rationalize, I get 2 plus an, and I get minus an squared over, okay. That doesn't seem ideal. Okay, so we scratch that. So that doesn't seem to be working. Let's try induction again. Can we do it by induction? If n is equal to 1, so we have a starting point, right? What's the base case? So if n is equal to 1, is it true that a1 is less than or equal to a2? Well, let's see. We know what a1 is. a2 is the square root of 2 plus a1. Okay. And let's see. Well, we know that a1 is certainly bigger than 0, right? So this is bigger than simply root 2. And root 2 is a1. Okay. Got that. So now if we assume that ak is less than or equal to ak plus 1 for some k. Well, then what would be the next step? So the next step, if we would assume this here, right, we increment by 1, right? Going from 2 to 3, we increment by 1. So we want to show, the next step would be to show that ak plus 2 is bigger than or equal to ak plus 1. So we say, okay, ak plus 2. By definition, it's 2 plus ak plus 1. But we've assumed that ak plus 1 is bigger than or equal to ak. But root 2 plus ak, that's ak plus 1. Done. Okay, so using this technique of induction, we can show that it's bounded above by 2. We can show that it's increasing. Okay, so it's increasing, it's bounded above. It has to have a limit. We have a theorem that says the limit is guaranteed. Okay, so how do we find that limit now that we know it exists? Well, here's a sneaky trick. We have this equality, right? Let's take the limit of both sides. Limit as n goes to infinity of an plus 1 should be equal to the limit. Well, I got a little bit ahead of myself, but let's do it. I've already wrote the square root. You can bring the limit inside the square root because square root function is continuous. Okay? And the kicker here is that this limit, okay, that's L, right? L is the limit as n goes to infinity of an. But, I mean, that's going to be the same limit here, right? Because here you're just incrementing by 1. You get to the same place. If n is going to infinity, so is n plus 1. So L is equal to the square root of 2 plus L. Got to solve for L. Square both sides. L squared is 2 plus L. So L squared minus L minus 2 is 0. So let's see, L minus 2, L plus 1. Two possibilities for the limit. Well, it's certainly not minus 1 because all of the terms are positive. So looks like the limit should be 2. All right, so we're going to move on now from sequences to series. Now, in a sense, a series is just a special type of sequence. It's a new sequence that's built from an old sequence. Maybe more correctly, a series is the limit of this new sequence. Let me explain. So start with some sequence. Okay, so we have a sequence, let's say A1, A2, A3, A4, A5, and so on. I'm going to write out the terms. Okay, so as an example, we could do the sequence 1, 1/2, 1/4, right? So in general, this is just a geometric sequence, right, with ratio 1/2, 1 over powers of 2. And now what we're going to do is we're going to form the so-called partial sums. Okay. So S1 is just A1. S2 is the sum of the first two terms in the sequence. Okay. S3 will be A1 plus A2 plus A3. S4 will be A1 plus A2 plus A3 plus A4, and so on, right? So in general, we could say Sn would be the sum k going from 1 to n of ak. Okay, sum of the first n terms. Okay. So this gives me a new sequence, right? This is a sequence, okay? And if you have a sequence, then it's reasonable to ask, does it converge? And, well, what would be the limit of that sequence, right? What should it mean to say, okay, well, what would it converge to? What would be that limit? If that limit exists, what does it look like? It's the limit n going to infinity of this Sn. Well, maybe we write that as the limit n going to infinity of this sum, k going from 1 to n of ak. And it's sort of notationally convenient to say, well, really what we mean then is something like this. It's the sum, k going from 1 to infinity of a sub k, right? We just keep adding the terms forever. Okay, so this notation that you see here, this is what we would call a series. Okay, so a series is the sum of a sequence. Okay, now for a lot of sequences that, even sequences that converge, a series is not necessarily going to converge, right? In particular, we can see right away that if the terms in the sequence are not shrinking and not shrinking fast enough, right? For example, if all the values in this sequence are staying close to some value like, say, 2, right? Then this is like 2, 2 plus 2, 2 plus 2 plus 2, 2 plus 2 plus 2 plus 2, right? If you keep adding more and more terms and those terms are always close to 2, well, then this sum is going to explode on you, right? The sum gets bigger and bigger and bigger. It doesn't have a limit. So it may not converge, right? So when we're studying sequences, we can use a lot of sort of calculus techniques. We can play around. We can often, use analytic arguments to say, oh yes, this sequence converges, and it converges to a particular limit. Here we just calculated it. Series is a very sort of different approach. The flavor is much different. The feeling is different, because when you're dealing with series, it's rare that you can actually say what a series converges to. This happens to be one where we can, so maybe it's a bad example. But a lot of the time, you're just trying to show that a series converges. You want to show that this sum, right, the limit of this sum is finite, that you actually get a value out. You may never be able to calculate it. It might be that all you can do is say that the limit exists. It has a value. We don't know what it is, but it exists, right? That can be frustrating for some people. It's a change in process from a lot of what you've done. The only thing you've seen so far that's similar to it is probably when you're doing like comparison tests for improper integrals. So it's a bit of an adjustment, but hopefully it's one that you're able to make. Coming back to this one here, let's see what those partial sums look like. Why not? S1 is 1. S2 is 1 plus a half, which is 3/2. S3, 1 plus a half plus a quarter. So let's see. That is 4 quarters plus 2 quarters plus 1 quarter, 7 quarters, right? S4. 1 plus a half plus a quarter plus an eighth. 1 plus 2 plus 4 plus 8. I get 15 over 8. Okay? S5. 1 plus a half plus a quarter plus an eighth plus 1 over 16. And if you add that all up, you find that you get 31 over 16, right? You get 2 minus 1, 2 minus a half, 2 minus a quarter, 2 minus an eighth, 2 minus a 16th, and so on. And so you might guess that this pattern continues. Of course, you should actually show it, and there are ways to show it, and we'll do that later on. But each of these partial sums, these are called partial sums, right, is 2 minus a number, and the number that we're subtracting gets smaller and smaller as we go through the partial sums, which makes you think that, hey, maybe, just maybe, this adds up to something, right? And actually, you can sort of see it visually, right? If you think about taking the number line from 0 to 2, there's 1 in the middle, and you start filling it up, right? Well, at the first, and so you always fill half of what there is to fill, right? So in the first step, we add 1, right? In the second step, we add a half. In the third step, we add a quarter. That's half of what's left over. In the fourth step, we add an eighth. Then we add a 16th, right? So you get this sort of like Zeno's paradox style thing going on. At each step, you cover half the distance that's remaining, right? So you go half the distance remaining. So there's always a little bit remaining because you only cover half the remaining distance, right? But each time you recover half the remaining, every time you cover half the remaining distance, you get a little bit closer and closer and closer to 2 until the distance that's left is so small that it's less than, let's say, epsilon, for example, if you're thinking about doing epsilon n definition for a limit. And so indeed, you can show that the limit actually converges to 2, and the sum, k going from 1 to infinity, actually we started at 0, right? 1 is 1 over 2 to the 0. 1 over 2 to the k comes out to be 2. Pretty cool. All right, so in the last video, we introduced the idea of a series as this limit of a sequence of partial sums for some pre-existing sequence, right? So if that limit exists, we say that the series converges. If it doesn't exist, we say the series diverges. So here are two series that we want to show diverge. So how do we do it? Well, we can start thinking about what do the partial sums look like, right? So in this case here, we have S1. You can even start at 0, right? S0 is 0 squared, 0. S1 is 0 squared plus 1 squared, which is 1. S2 is 0 squared plus 1 squared plus 2 squared is 5. S3, 0 squared, 1 squared, 2 squared, 3 squared is 14, and so on. And it certainly seems like those partial sums are going to keep growing and growing and growing. Well, in general, we know that Sk is the sum, let's say n going from 1 to k. Might as well start at 1, right? Starting at 0, we're adding 0. We don't gain anything from that. N going from 1 to k of n squared. Oh, we've seen that before. Way back when we were doing like Riemann sums, right? We saw this summation formula. Maybe we did it with I instead. We get something like k plus 1, 2k plus 1 over 6. And so certainly we can see from this that if we take the limit as k goes to infinity of sk, well, that limit is going to be infinite, right? This thing grows more or less as k cubed. Okay, so certainly the limit doesn't exist, so the series diverges. All right, how about this one here? Well, let's start writing out, what does the sequence look like, right? So Bn looks like, well, if n is equal to 1, this is minus 1 squared, so 1, and it's going to be minus 1, 1, minus 1, 1, minus 1, 1, right? Forever. Okay, so from there, well, what does Sn look like? Well, we just do 1, and then 1 minus 1, we get to 0. 1 minus 1 plus 1, 1. 1 minus 1 plus 1 minus 1, 0. And I think by now you can probably guess the pattern. We get something that looks like that. Okay, so no fancy formula this time. We just look at this and say, well, look, we have a sequence which just alternates between 0 and 1. We want the limit of that sequence. Well, that limit certainly does not exist, right? The limit as n goes to infinity of Sn does not exist, so the series diverges. So the next example we want to look at, or topic, if you like, is geometric series. So the geometric series is a special type of series where we actually can understand pretty much everything there is to know about the geometric series. It's also an important series because it comes up quite a bit once we move on. Right? Later on, we're going to look at power series, Taylor series. Right? We're going to have, so power series is sort of a natural extension, from polynomials to things where we're still working in powers of x, but we don't have a highest power of x. Right? We just keep going on forever, adding more and more terms. In which case, well, you're going to have like an x to the n in there. And you want to understand what's going on, right? You're going to be seeing series that look like that, okay? Some people will put a constant in there, like an a times r to the n, and call that a geometric series, but you can always factor out the constant, bring it out front. Even for an infinite series, that works. So we'll just concentrate on this, and if we want to put a constant in, we can always multiply by a constant. All right. So what can we say about a geometric series? Well, one, notice that we start at 0, not at 1. Okay? So if we were writing out the terms in the sequence that we're using here, right? The terms in the sequence are 1, r squared, r cubed, and so on. We add by r every time, so we can think of those as maybe like the ANs. And then the SN, right? The partial sums that we're adding up. Those are going to be 1 plus r, 1 plus r plus r squared, 1 plus r squared plus r cubed, and so on. Okay. Now, what's cool is we can actually come up with a nice closed form formula for those partial sums. Okay. So we have the following. So if we look at Sn, so Sn would be 1 plus r squared, okay, up to r to the n. All right? Now, I'm going to do this. I'm going to do r times Sn, multiply everything by r. So then I have r plus r squared, and r cubed, and so on, up to r to the n. And then n plus 1. Now I've shifted it over 1 because what I want to do is I want to subtract these. Subtract. So on this side, if I subtract, I'm going to have 1 minus r times Sn, right? 1 Sn minus r Sn gives me 1 over r if I factor out the Sn. And on the other side, I have 1 r minus r squared minus r squared, rn, right? All of these terms cancel. We're just left with that last one, r to the n plus 1. Okay? So that means that my partial sums look like this. 1 minus r to the n plus 1 divided by 1 minus r. Okay? And notice that the dependence on n is entirely here in this exponent. Okay? So now we ask ourselves, well, what happens? What happens if you take the limit as n goes to infinity of r to the n, or n plus 1 if you like? Okay? Well, there are three possibilities. And I guess, just to keep things simple for now. No, we'll just say, let r be a real number. If the absolute value of r is less than 1, okay, then this limit will be 0. Okay? Because if you take a number that's less than 1 in absolute value and you raise it to a higher power, it gets larger and larger and larger, and you get 0 in the limit. Okay? It's equal to 1 if r is equal to 1. It's undefined if r is equal to minus 1, because it's just going to flop back and forth between 1 minus 1. And it's going to be infinite if the absolute value of r is bigger than 1. Okay? All right. So these are not too hard to work out. You can convince yourself that these are true. And so then we look at this and we say, okay, well, what can we say then about this sequence of partial sums? Well, minus 1, actually, we saw that in the last video, right? We saw that as an example. Minus 1 to the n, that series diverges, right? We don't get anything there. So that one diverges. 1 to the n also diverges, right? Because the one, I guess, case that we left out here is this is all well and good if r is not equal to 1, right? But if r is equal to 1, then Sn is just n, right? Because you're just going to be doing 1 plus 1 plus 1 plus 1 plus 1, right? So you get n. And the limit of n as n goes to infinity is certainly infinite. Okay? And so we look at this and we say, well, you know what? The only time where you can actually take a limit of this is going to be if absolute value of r is less than 1. So what we can say is that this geometric series, n going from 0 to infinity, r to the n, it converges if the absolute value of r is less than 1. And in that case, we get an answer, 1 over 1 minus r for that sum, right? Because this part is going to go to 0. Okay? And it diverges otherwise. So this is an interesting example because not only can we say exactly when it converges, we can say what it converges to. That's not always going to be the case. All right, here are 3 quick examples. 3/4 to the n, minus 1 to the n over 2 to the n, 3 to the n. We want to identify these as geometric series, decide if they converge. If they do converge, figure out what the value is. Okay? So in this case here, it fits the pattern, right? We say, okay, what is the value of r? R is 3/4, and 3/4 is definitely less than 1 in absolute value. So we know that it converges, and we know what it converges to, right? The sum, and going from 0 to infinity. Maybe I'll point that out. It converges, and so let's figure that out. So 3/4 to the n, okay, it's going to converge to 1/1 minus r. R is 3/4. So 1/1/4, if we simplify, we get 4. Okay, moving on to the next one. Well, one of the things that you need to realize here is that I can always rewrite that as -1/2 to the n, right? Same as this one here, we could have equally well been given this one as 3 to the n divided by 4 to the n. So you got to be able to, do those basic laws of exponents manipulations to get things into the right form. All right, it's in the right form. So what's r? R is -1/2, and we know that the absolute value of -1/2 is 1/2, which is less than 1. So again, we have a convergent series, and what is the sum? N going from 0 to infinity of -1/2 to the n. It's going to be 1/1 minus -1/2. Okay, so 1 plus half, so 1/3/2. Take the reciprocal, we get 2/3. Okay. This last one here, well, r is equal to 3, that's bigger than 1, so that diverges. So the next type of series we want to look at is a p-series. Okay, so the basic form of a p-series looks like this. It's just 1 over some power of n, right? P is the power here. P in p-series is the power of n that we see in the denominator. We can consider a basic p-series where we simply have a power of n. We might see something more general like this where we have some coefficients in there. The only thing you got to be careful about here is the starting point. I've written n equals 1, but we'd have to check to make sure, so A and B here, I mean, they could be any real numbers, but we'd have to check to see when does an plus b, when does that equal to 0, right? We want to watch out for that. Make sure it's not equal to 0. If there is a 0 for this at a positive value for n, right? If there's an integer value of n that gives me a 0, I better start my series after that, or it's not going to be defined, right? So we won't even get to talk about convergence because there's going to be one term in the series that blows up. All right, so the main result about p-series is the following theorem. Which states that a p-series converges if p is strictly greater than 1 and it diverges otherwise. So it diverges for p less than or equal to 1. Okay, so that's simple enough. Now, this p-series test tells us whether or not the series converges. It doesn't say anything about what that series converges to, right? So this is strictly a test for convergence. We are not trying to calculate a value for the series. Should remind you a little bit about the p-series test for improper integrals, and in fact that's where we get this from. We'll see in the next section that we can use the result that we have for improper integrals to establish this result for p-series. So the proof of this result is going to have to wait, but in the meantime we can put it to use. Here are several series. We can see, do they converge or diverge? This one here, this is actually an important result. This is the so-called harmonic series. Okay. And in this case, p is equal to 1, but it's not bigger than 1. So this diverges. Okay, so the harmonic series is sort of a famous counterexample, right? The first thing that you might kind of think when you start working with series, you're adding infinitely many terms, so you might think that as long as the terms go to 0, you should be able to add them all up. But the harmonic series is this classic example that shows it's not enough to have the terms in your series go to 0. That's not enough for you to have a sum. You actually need those terms to go to 0 fast enough, or the thing is not going to converge, right? And so we can think of this as a consequence of the p-series test that this series diverges, although there are other ways that you can do this. You can prove divergence sort of directly. The classic way that you do this is you say, okay, well, my sequence looks like 1 plus a half plus a third plus a quarter plus a fifth, and so on. And you start sort of grouping things together, and you say, okay, well, these two terms, they add up to something that's bigger than a half. And then actually, if I added the next sort of 3 terms, a fifth plus a sixth plus a seventh, those are going to add up to something that's bigger than a half, and so on. I think this is the strategy that we use. And so by sort of grouping things appropriately, we can say, well, the whole thing is bigger than 1, plus a half, plus a half, plus a half, and that's going to go to infinity if you keep adding 1/2 forever. Interesting. This next one, well, this is p-series with p equal to 2, so this converges, right? Here, p is equal to 2, so this one converges. This one is another famous series because we actually can say what the sum is. And the sum is sort of surprising. Hope I remember this correctly. The result is something like pi squared over 6. And you might be surprised to see pi making an appearance there. And there are a number of ways that you can derive this result. In different areas of mathematics, it pops up. You can show it using, surprisingly enough, complex numbers, complex analysis. There's one way to show it. There's other ways coming from differential equations. There's also, it's a strange result. It pops up in a number of places. There are 3 or 4 very different proofs of the result. The original result, I think, goes all the way back to Euler. And so that's interesting. Maybe more interesting, as far as I know, if we go to 1 over n cubed, nobody actually knows what that adds up to. We know it converges, right? It's a p-series with p equal to 3. P is bigger than 1. It converges. Nobody knows what it converges to. Odd. How about this one? Okay, this is, well, root n is 1/2. So it is a p-series, but p is equal to 1/2. And 1/2 is smaller than 1, right? 2 is bigger than 1. We should have pointed that out. And so that means that this one diverges. Okay? This one here is not a p-series. We actually can't comment on the convergence of this one yet. When you have this minus 1 to the n, this alternating sign, right? So the terms in this series are going to alternate between positive, negative, positive, negative, positive, negative as you add them up. Those series have a special name. They're called alternating series, and there are special techniques for dealing with them. It turns out that this alternating series does actually converge. So adding that alternating sign is enough to take this divergent harmonic series and give you a convergent alternating series. It does converge. And actually, interestingly enough, we know what this converges to as well. Converges to the natural log of 2. That's weird, right? Actually, we're going to see once we get to talking about Taylor series, we'll see where that comes from. Okay? So it's not a p-series, but we'll see later on how to show that one converges. This one here, oh, this is a p-series, right? It's a sort of this general form of a p-series with p equal to 3, which is bigger than 1. And so that means that this one converges. Notice the starting value, 11, right? We can't do 10 because we'd get a 0 in the denominator. So we got to make sure that we watch out for things like zeros in the denominators. Start the sum a little bit later on once you're past all the zeros, and then you can talk about convergence. Last one, well, the last one is not a p-series, the last one is geometric series. Fortunately, we've already done that, right? This is geometric. It's not a p-series, but it's geometric. With r equal to 1/2. And of course, 1/2 is less than 1 in absolute value. So we know that this converges. And actually, we know what it converges to. We saw this in the introduction video. Converges to 2. So the next few examples we're going to look at deal with what are called telescoping series. So a telescoping series is one where, as we write out the partial sums, we find that there's a lot of cancellation. So there's a lot of cancellation within the sums, and that allows us to evaluate the series, right? Now this one here, we could show that this converges using essentially p-series or comparison. We haven't established comparison tests yet, but if you really wanted to, you could do something like this, right? You could write this as the sum n equals, 1, get it over common denominator, n minus n plus 1, and then we subtract n. We just have 1 over n times n plus 1, right? And so that's roughly 1 over n squared, p-series, p equals 2, bigger than 1, converges. So we're pretty sure it converges. But we don't necessarily know what it converges to. So here's where we can kind of play around with this, and we say, okay, well, let's start looking at the partial sums. S1, 1 minus 1/2. Okay. S2, we get 1 minus 1/2, right? There's the n equals 1 term. Now we add the n equals 2 term. 1/2 minus 1/3. S3, we have 1 minus 1/2 plus 1/2 minus 1/3. And now we go for the n equals 3 term. 1/3 minus 1/4. And maybe now you can sort of see what's going on, right? We could regroup this as 1 minus 1/2 plus 1/2, so 1/2 minus 1/2 in there, right? Minus 1/3, so 1 minus 1/3, right? Here we can regroup this as 1/2 minus 1/2, right? And then 1/3 minus 1/3, right? And then minus 1/4. So we get 1 minus 1/4, right? And you can probably guess what's going to happen for the next one, right? So in general, if we went down to Sn, we would have 1 minus 1/2, and then plus 1/2 minus 1/3, and then plus 1/3 minus 1/4, and so on down to, well, so the very last term will be 1 over n minus 1 over n plus 1. And of course, just before that, there would have been a minus 1 over n, n minus 1, so on. And so basically everything cancels, right? There's a 1/4 there that will cancel with that. Those will cancel, those will cancel. And you just get 1 minus 1 over n plus 1. All right. Well, now we know what we get, because we know that a series is just equal to the limit of the sequence of partial sums, right? So it's the limit n going to infinity of 1 minus 1 over n plus 1. That's going to go to 0. So we get a limit of 1. Okay, here are 2 more examples. We'll start with this one. Now, this certainly doesn't look like a telescoping series, but remember the previous one, I pointed out, they had given to us as 1 over n, subtract 1 over n plus 1, I think it was. that if you put it over a common denominator, then you get something that looks like this, right? We said, hey, you can sort of do like a p-series sort of thing on it if you wanted to. But of course, you may also need to reverse that process. So we might have to say, okay, let's work over on the side and say, okay, we've got 2 over n times n plus 2, right? Rational function. We can do partial fractions. A over n, b over n plus 2, right? So how do we solve for these? Remember, if we multiply everything by n, we have a isolated, put in n is equal to 0. This disappears. It's gone from there. Putting n equal to 0 gives 2 over 2. So a is 1. If I multiply everything by n plus 2, this will disappear when we plug in minus 2. That'll just be b. This is gone. Put in minus 2. 2 over minus 2. b is minus 1. Okay? So we can rewrite this as the sum, n going from 1 to infinity of, sorry, something fell off the light. Still working. Let's keep going. 1 over n plus 2. All right. Start writing out the partial sums. See if we can figure out what's going on. Okay, so we have, let's just write a kind of a general one. What is it going to look like? Sn. Okay, so n equals 1. I have 1 minus a third. Then let's go to 2. 1/2 minus a quarter. Oh, it doesn't look promising, does it? Oh, but let's go to 3. A third minus a fifth. Let's go to 4. A quarter minus a sixth, and so on. So we actually do get some cancellation. We eventually get some cancellation, right? The 1/3 cancels with the 1/3. 1/4 will cancel with 1/4, right? That 1/5 is going to cancel with the 1 over 5 in the next one. The 1 over 6 is going to cancel with something in the next one. But the 1/2 survives. So we get 1 plus a half, and pretty much everything else is going to cancel down to, well, we're going to have a couple terms left over, right? And that was going to be, that's from n equals 4. Yeah. So we have 1 over n plus 1. So simplifies down to there, okay? And if n goes to infinity, well, these are going to go to 0, and those stick around, right? So if we take the limit as n goes to infinity, we're just left with 1 plus a half. So we get 3 over 2 for the limit. Okay, come to this last one. Well, that definitely doesn't look like harmonic, or sorry, telescoping series. But maybe we can do something with it. Can we do something with it? Ah, yes, log properties, right? We know that log of n plus 1 over n, okay, is the same thing as log n plus 1 minus log n, okay? So that means if we start writing out the partial sums, right, Sn, right, it's going to be, well, first of all, log 2 minus log 1, which is just 0, right? Plus log 3 minus log 2, right? Then it's going to be log of 4 minus log of 3, and then log of 5 minus log of 4, and so on, down to log of n plus 1 minus log of n. Okay, so now we look for cancellations, right? Log 3 cancels with log 3. Log 2 cancels with log 2. Log 4 is going to cancel with log 4, right? The next term would be log 6 minus log 5. Log 5s cancel. Actually, everything cancels except for that. So the nth partial sum is the natural log of n plus 1. Okay? But if we let n go to infinity on that, we don't get a value, right? It's infinite. So this diverges. It diverges. If you like, you might add it diverges to infinity, but the main point is it diverges. All right. We have 3 series here on the board that we want to try to evaluate. The strategy for all of these is going to be to work with some basic properties for a series and a few known results, some of which I've mentioned previously, some of which are summarized in the textbook. We'll point them out as we go. So a couple of the properties that we are going to rely on here are going to be things like if you have the series of a sum, you can write that as a sum of a series. So sum of the ANs, sum of the BNs. And if you have a common constant multiple, say C times AN, inside the series, you can factor it out. Okay. And the reason you can do that is that, well, for each of the partial sums, right, for a partial sum, it's just a constant multiple. You can factor it out. And then the series, of course, is the limit of that sequence of partial sums. And we know that for limits, if you have a constant multiple inside the limit, you can bring it out. Similar arguments will work here, right? We know that for finite sums, this is valid. We also know that the limit of a sum is sum of the limits, and so we can make that argument to get those things to work. Okay, so let's come to something like this. N going from 1 to infinity, we've got minus 1 to the n squared minus n over n cubed. How are we going to deal with it? Well, let's try manipulating a little bit first. So n going from 1 to infinity. Let's leave that minus 1 to the n plus 1 out front. And notice that we can divide each of these individually by n, right? So n squared over n cubed is just 1 over n. N over n cubed is 1 over n squared. Okay, so we can split it up like that. So then we can write this. If we multiply that through, and we split this up into 2 series, we can write it like this. Minus 1 to the n plus 1 over n. Subtract sum, n going from 1 to infinity, minus 1 to the n plus 1 over n squared. Okay? Now, each of these turn out to be known results, and these are not things that you're supposed to know how to come up with or establish at this point. They're just results that somebody somewhere in the past has proved. They're given to us in the textbook as a list of known values, and so we're just going to use them. This first one here is the natural log of 2. I think I've got that right, the minus sign. Might be off by minus 1, but no, I think that's right. And this one here, it turns out that this one is pi squared over 12. Why? I don't know. There's some fairly sophisticated mathematics that probably goes into establishing that well beyond what we're doing in this course. But there you have it, right? You can get that answer. How about something like this? Well, we can use the constant multiple rule, and we can write it as 1,000 times the sum, n going from 1 to infinity, of 1 over n factorial. Now, one of the known results that's given to us in the book says that if this sum started at 0, the sum going from 0 to infinity of 1 over n factorial is actually equal to e, to Euler's number. So the sum is starting at the wrong point, but that's okay. We can modify that. We can say, all right, if I started this sum at 0, Well, what does the n equals 0 term look like? The n equals 0 term is just 1 over 1 over 0 factorial, which is just 1, right? So by starting the sum 1 earlier, I've added 1. So I can subtract 1 to balance. Okay? And then I know that this is e, and that's, well, minus 1. Okay? So we can get that answer. Again, we will actually see later on why this is equal to e. Once we've done power series, Taylor series, we'll see why that's equal to e, but we're not there yet. All right, this last one. Well, what do we have? We have 1 over 4 squared plus 1 over 5 squared plus 1 over 6 squared, 1 over 7 squared. So we've got the sum n going from 4 to infinity of 1 over n squared. Okay, well that is the same thing as the sum n going from 1 to infinity of 1 over n squared if we subtract off the n equals 1 term, the n equals 2 term, and the n equals 3 term. Sorry, 3 squared is 9. Right, oops, there. I'll get it right eventually. Okay, and this 1 over n squared, that's that result we've mentioned already. This is pi squared over 6. And this here, I mean, I guess if we want to get the common denominator, 36, do we really want to do it? Why not? 36 minus 9, well, let's add them. 36 plus 9, 45 plus 4, 39. Sorry, 49. 49 over 36 for our answer. All right, so in the previous videos, we introduced the notion of a series, an infinite series is the sum of the terms in a sequence. We talked about convergence and divergence. We gave a couple of examples of series where we can actually compute the sum. So we talked about geometric series, we talked about telescoping series, and we saw how to decide whether or not those converge or diverge. We also introduced the p-test for convergence of a series, although at the time we didn't really have a justification for it. Now we start getting into some of the tests for convergence that will let us decide whether or not a series converges or diverges, right? Now these tests are not going to help us find the value for a series if it does converge. They're simply going to answer this question, yes or no, does it converge? The first one is the integral test. So here's the statement of the integral test. So we start with the function. It does have two requirements, and if you are going to apply the integral test, it's important that you confirm that these requirements are verified. The function has to be positive, and it has to be decreasing. The one place where there's maybe a little bit of flexibility here is you could always replace this number 1 by some other value. Maybe replace that by some integer k. Maybe you want to start at 0. Maybe you have a function that isn't decreasing everywhere, but for x bigger than or equal to 10, it is decreasing. Well, then maybe you want to start at k is equal to 10, right? And then, of course, if you make that change, you would make the corresponding change down here and here, okay? So we do this standard thing where we've talked about this with sequences. We can always define a sequence. If we have any function that's defined for at least all positive real numbers, we can restrict the domain to the natural numbers, and that gives us a sequence. So the integral test says that convergence of the series, where we sum the terms in this sequence, convergence of that series is equivalent to convergence of the corresponding integral, right? So the if and only if is saying, well, if this converges, so does this. If this converges, so does this. Or if you want to put it another way, if this diverges, so does this, right? So we look at this integral. If it converges, we know that this one converges. If it diverges, we know that this one diverges. And the idea here is we already have some practice with improper integrals and figuring out whether or not improper integrals converge or diverge. And so anything that we learned about improper integrals and convergence of improper integrals can now be applied to convergence of series as long as we can put our series in this form for the appropriate type of function. Now, if you want to see why this works, it's actually pretty simple. All right, let's draw some coordinate axes. Let's draw a function which is positive and decreasing. Something like that. Okay. And of course, it needs to decrease to 0. I mean, it's not in the statement of the theorem, but we know that if it doesn't decrease to 0, we know that this is not going to converge, and we know that that's not going to converge. So better decrease to 0, right? And now we can mark off all the integer points. 1, 2, 3, 4, 6, 7, 8, 9, and so on. All right? And we can think about area under the curve, and we can think in terms of Riemann sums, all right? So we're going to do, so we can think about doing now, I mean, we really shouldn't talk about Riemann sums when we're talking about improper integrals because Riemann sums need a closed interval to work with. But we can just go with sort of a fixed, delta x equals 1. So we look at intervals of length 1, all right? And if we do, say, left endpoints, remember that when we do a Riemann sum, we can choose where on each interval we want to pick our point. So if we do delta x equals 1 left endpoints, well, then we get something that looks like this, right? Okay, and so on. And so one of the things that you can see right away is that, well, what are these values, right? This is the point 1, f of 1, right? This is the point 2, f of 2, and so on. The sum that we get, right, we get the sum, and going from 1, and I guess we can continue all the way to infinity, of f of n, but f of n is just an, right, times delta x, but delta x is just 1. So we get the series, actually, right? And what this is saying is that that series, well, that must be bigger than the corresponding integral, right? Okay? Because we can see that we have a little bit extra in each rectangle. So if we knew that this integral diverges, if we know this integral diverges, well, then certainly this series has to diverge as well, right? Because if this is infinite, so is that, because it's bigger, right? But, you could equivalently decide that you're going to do maybe delta x equals 1, but you want to do right endpoints, right? So then we would get the underestimate, right? We use right endpoints, so we get that. Okay. And so if we use right endpoints, well, then again, this would be kind of f of 2. We're using f of 3 for the second rectangle, f of 4 for the third, and so on. So we actually get, we still get the sum of an, but actually n starts at 2. Okay, n starts at 2. And that amount is going to be less than the integral. Okay. All right. Now that's not quite our series, but if the sum starting at 2 converges, well, then certainly the entire sum converges because we can always just add, right? We can just do this. We can say, okay, that's fine. Just add a1 to both sides. Now you have the series, right? This is n equals 1 to infinity of an. And of course, if this integral converges, adding a number to it is not going to change the convergence of the integral. So if this converges, this value is finite. This is less. So we expect that it should converge as well, right? And yes, I mean, I guess all this really, if we don't put any conditions on the function, this just tells us that, well, this number is not going to become infinite. Maybe that doesn't mean that the series is going to converge because, what if the values bounce around a bit, right? Well, that's where, the function, we're saying the function has to be positive, right? So that means that all the ANs are positive, so we can't have some series that oscillates back and forth, because if we're jumping back and forth, we'd have to be adding negative values. We're not allowing that, right? And we need the decreasing condition as well, again, just to make sure that everything fits together the way it should. But that's the integral test, right? So the way you apply the integral test is somebody hands you a series, says, does this converge? Well, you look at the terms in this series and you say, okay, can I identify those terms with the values of some function? If I can, does the function have these properties? Or does it at least eventually have those properties? If it does, then you look at the corresponding improper integral. Hopefully it's one that you know how to evaluate, or at least decide on the convergence of. And if you can decide whether or not the improper integral converges or diverges, well, then you can apply the theorem and you know whether or not your series converges or diverges. All right, so here's our first example where we're going to apply the integral test to determine the convergence, or I guess, well, determine the convergence of, so we decide if it converges or diverges, right? So we're going to determine the convergence of this series. Does it converge? Does it diverge? All right, so we make some identifications. We say, all right, the terms are natural log of n over n squared. That's what an looks like. And we can write that as f of n, where our function f of x is the natural log of x divided by x squared. So we got to check our conditions, right? Is it positive? It's positive as long as the natural log is positive, and that's true as long as x is bigger than 1, right? Log of 1 is 0. So the first term in this series is actually 0. So really we should say that n starts at 2, right? We can put n equals 1 in there, but the n equals 1 term is 0. We're adding 0. It doesn't change anything. Is it decreasing? How do we check if it's decreasing? Well, we could appeal to the definition and say, okay, I'm going to show that if x2 is bigger than x1, then f of x2 should be smaller than f of x1, right? There are sort of these difference tests or ratio tests that you can apply to the sequence to see, but it's a function of x. It's a differentiable function of x. We know how to decide if a differentiable function of x is decreasing. We look at the derivative, right? Let's look at the derivative. F prime of x is going to be, well, let's do quotient rule. Derivative of the top, 1 over x times x squared, minus derivative of the bottom times the top, divided by the bottom squared, x to the 4. So this is going to be x times 1 minus 2 log x over x to the 4. Okay, we need this to be negative. When is this going to be negative? It's going to be less than 0. Well, it's going to be less than 0. See, well, x can't be less than 0, right? It's a natural log. Negative numbers aren't in the domain. So it's going to be less than 0 if 1 minus half log x is less than 0. Sorry, 1 minus 2 log x is less than 0. And that's if, let's see, that's if the natural log of x is bigger than a half. And that's going to be true if x is bigger than or equal to 2. Natural log of 2 is like 0.6 something, I think. Okay, so we're good to start at 2, right? Remember, we don't necessarily have to start at 1 in the statement of the theorem. We can start at some k if we want to. All right, so we know that the theorem applies. So now we look at the integral. Okay. Let's do that in green just so it stands apart from that. We need to look at the integral from 2 to infinity. We can do 1 if you want. Natural log of x over x squared times dx. Okay. Got to integrate by parts for this one. Let's kind of do that over on, let's do the indefinite integral over on the side, just to remind ourselves how that goes. So if we have a natural log, that's always our u, right? So u is log x, du is 1 over x, dv, 1 over x squared dx, so v is minus 1 over x. Okay, so we get minus log x over x plus the integral of v du, right? So plus the integral, plus because of the minus sign there, plus the integral of 1 over x squared. Okay, so we get minus log x over x minus 1 over x, and I mean plus your c if you want to put the c in there. Okay, so that means that this integral will be, it'll be the limit as, so let's say n goes to infinity of minus log n over n minus 1 over n. Okay, that's the upper limit. Plug in the lower limit, 2 log 2 over 2. Okay, plus 1/2. And we just check now that this limit here is 0. Right? Certainly that goes to 0. One application of L'Hopital's rule tells you that that one goes to 0, right? Because derivative of the top gives you the 1 over n, derivative of the bottom gives you 1. And so we know that that limit is just 0. So we get this finite value for the integral, right? Integral converges. And so we can state our conclusion. We can say, since the integral log x over x squared it was, sorry. Since that converges, so does the sum n going from 1 or 2 if you want, 2 to infinity of log n over n squared. Okay, by the integral test. All right, so next we're going to prove a result that was promised in the previous section, and we're going to prove the p-test. We'll do it in general. Of course, you can set a equal to 1, b equal to 0, and get the regular p-test. But we'll do the general version because, of course, that if we prove it in general, it's going to apply to the special case as well. One thing that we should probably require, though, I think, just to, well, certainly I think we should specify that a is positive. If a is equal to 0, then these are just constants, and then we're adding up a constant, and it's going to diverge, right? So we need a to be positive. If a was negative, well, you could factor the minus sign out. You get a minus 1 to the p. It's either plus or minus, right? It's constant multiple. We don't worry about that. And also, just to simplify things for us, let's assume that b is bigger than or equal to 0, okay? We'll assume that as well. Because if b is negative, then we introduce the possibility that there might be a 0 in the denominator for some value of n. And even if that 0 in the denominator doesn't occur at an integer, even if it occurs at some rational value, or I mean, these could be real numbers, right? It could be some real number value. It would still be the case that there's a vertical asymptote somewhere, right? And if that vertical asymptote occurs somewhere between, like, let's say it occurs between n equals 5 and n equals 6 or something like that, well, we won't have a positive decreasing function until we cross the vertical asymptote. So we can handle that. We just modify things, right? A finite number of terms doesn't affect convergence. We can always start at some other value. But just to keep life simple, assume that b is bigger than or equal to 0, so we don't have to worry about an asymptote, okay? At least we don't have to worry about an asymptote that happens for positive values of n, right? Okay, very good. So with that in place, basic graph transformations should tell you what this thing looks like, right? The graph of, let's see, so what are we going to do? Well, first of all, our a sub n, looks like 1 over a times n plus b to the power of p, right? And so that is equal to f of n for a function f of x given by 1 over ax plus b to the p, okay? And that's just some transformed version of 1 over x to the p, and 1 over x to the p, assuming that p is positive here, right, typically is going to look like that, right? This half will either be here or there, depending on whether p is odd or even. Get something that looks like that. So we get the positive decreasing function that we're supposed to have. So we look at the integral. We say, okay, what do we get? Let's do the indefinite integral first. So 1 over ax plus b to the power p, integrate with respect to x, okay? Now, we know that if p is equal to 1, well, then we get, this is going to give me 1 over a times the natural log of ax plus b. And we know that as x goes to infinity, that's going to blow up on us, okay? So we know it diverges if p is equal to 1. So we're going to assume here that p is not equal to 1. Well, if p is not equal to 1, then this is just power rule, right? Power rule and chain rule. So that is, so this is the integral of ax plus b to the minus p. We add 1 to the exponent, so we get minus p plus 1, 1 minus p. If we drop that into the denominator, that's going to be ax plus b to the p minus 1. 1 over that. Oh, but we also have to divide by a, right? There's a 1 over a coming from the chain rule. So there's an extra a out there. Okay. Plus your c if you like. Okay. And so if we're looking at the improper integral, so going from 1 to infinity, 1 over ax plus b to the p dx, okay? Well, we're going to get the limit as n goes to infinity, 1 over a times 1 over, oh, we also have to divide by, the new exponent, right? Forgot that, ha ha ha. So we also have a p minus 1 in there, or maybe minus 1 plus p. So we also have that. Right, yeah. So we have that. We have minus p plus 1. We have 1 over ax plus b to the p minus 1. There's our, or sorry, n. I guess I called it n. There we go. Minus the lower limit, if we plug in 1, what do we get at the lower limit? We put in x equal to 1, we get, some constant, right? Minus, we get 1 over a times a plus b times 1 minus p. It's a constant. And so we look at this and we say, yeah, this here limit, what can we say about it? This limit is going to be equal to 0 as long as p minus 1 is positive, and it's going to be equal to infinity if p minus 1 is negative, right? We've already ruled out the p is equal to 1 case. Okay, so it's going to converge if p minus 1 is positive, which is the same thing as saying that p is bigger than 1, which is what we had here, right? And if and only if, because if p is not bigger than 1, then either it's equal to 1 and we know it diverges, or it's less than 1 and we know it diverges. Okay? So either way, we know that we have a convergent improper integral if p is bigger than 1, and so correspondingly we have a convergent p-series if p is bigger than 1. So the next theorem that we want to look at is the direct comparison test. Okay? So we've stated it here as a theorem, and this is the sense in which is direct comparison right here. Okay? So this is direct comparison. So if you're able to set up a direct comparison, this is typically the simplest argument that you can give for convergence of a series, right? If we have one series which we know converges, and it's easy to show that the terms in some other series are always less than or equal to the corresponding terms in the convergent series, then this one must automatically converge as well. Conversely, if this series diverges, right, and the other series has terms which are larger, then it has to diverge as well. One thing that is important here is that they do have to be positive sequences, okay? The fact that they're positive, right, means that, well, if we let, let's say, Sn to be the sum n going from 1 to big N of an, and let's call the other one, I don't know, maybe T, just because it's the next letter in the alphabet. I call Tn sum n going from 1 to n of Bn. So if we define these, if we have that and that, then these sequences, Sn and Tn, well, they have to be monotone increasing, right? Because we started with positive sequences. So every time we add a new term, the sum gets bigger. Okay? So they're monotone increasing. This is a useful observation to make. One thing that tells us is that if we do have a divergent series, if this sum diverges, okay, well, it has to diverge to infinity, right? Has to diverge for infinity. The other thing we notice is that, well, Sn has to be always less than or equal to Tn. Maybe I should have used a different letter here. Let's call that n naught or something, okay? For n bigger than or equal to this n naught, right? So we always allow that maybe your comparison doesn't quite work at the beginning, but it works eventually, right? When we're talking about convergence of series, we always care about what happens eventually. First few terms aren't that important, right? First 100 terms, 1,000 terms, million terms aren't necessarily important. It's only what happens eventually that matters, okay? So maybe this is a big number. Doesn't matter. As long as we have this eventually, okay? So what that tells me is that, well, if the limit as n goes to infinity of Sn is infinity, then the limit as n goes to infinity of Tn must also be infinity, right? If we have this inequality for all n, right, this quantity is always bigger than that quantity. If this is becoming infinite, this one must also become infinite. You can prove that straight from the definition of the limit if you want. Okay. On the other hand, and so by the way, this proves the second part of the theorem, right? If Sn goes to infinity, right, that's saying that this series diverges, which tells us that this one diverges. On the other hand, if the limit as n goes to infinity of, let's say, Tn is some value, call it b. Why not? Well, what can we say then? Well, we know that Sn has to be less than or equal to Tn. But Tn has to be less than or equal to b, right? Because if Tn is an increasing sequence, right, it's an increasing sequence, it has to be less than or equal to its limit, okay? Because it gets bigger. As n increases, so does Tn, okay? Well, that means that this sequence is bounded and it's increasing. So what do we know about bounded increasing sequences? We have the monotone convergence theorem. It says if you have a bounded increasing sequence, it has to converge, okay? So that's exactly the scenario of the first, right? So that means that this sequence converges, which is the same thing as saying that the series converges, and that proves the first part. Okay. In case you're wondering why it's true, there's the argument. So direct comparison is pretty straightforward. It makes intuitive sense, right, that if these numbers are always bigger than those numbers, if this converges, well, this should converge to something smaller. Makes sense, right? Similarly, if this diverges, well, this should be bigger than that, so it should diverge as well. Makes sense. Next, we'll look at some examples so we can see how we actually apply this in practice, right? And the challenge with using direct comparison is here. It's getting that inequality. Right? It's easier said than done. Sometimes it's straightforward and you can see the inequality and you set it up straight away and everyone's happy. Sometimes it's tough. So we'll look at some easy examples, we'll look at some tough examples. And then just like for improper integrals, when direct comparison fails, you ask whether or not there's some sort of limit comparison that you can use, and fortunately the answer will be yes. All right, so here's a quick and easy candidate for direct comparison. All right, we want to decide if this particular series converges or diverges. You might say, hey, I know something about geometric series and when they converge. I also know something about p-series and when they converge. Here we seem to have the two of them sort of jumbled together. Well, what do? There's actually kind of two ways you could do this, right? You could say, well, here's one option. We could say, since 1 over 3 to the n plus n squared is less than 1 over 3 to the n. Why? Why is that true? Well, whatever n is, right, n squared is a positive number. If you add a positive number on the denominator, right, you're making the denominator bigger. That makes the whole thing smaller, right? So this should be a larger number over here. And we know that this converges. right? Well, we should probably say y. It's geometric with r equals 1/3, which is less than 1. Then we know that our series converges by comparison. That's it. That's all you got to say, right? But make sure you check the boxes. What are you comparing to? The thing that you're comparing to, why does it converge? It's geometric. Why do we know that the other one converges? Well, because we're using the comparison test, right? We should also keep an eye on the requirement that terms be positive, but we've got that going for us as well. Okay. Now, of course, you could have gone in another direction with this. You could have also said, hey, I don't need to compare to the geometric series. I could also compare. Right, this one gave us two options. We could have also said, hey, 3 to the n over n squared, for the same reasoning, is less than 1 over n squared, right? And I know that this series, n going from 1 to infinity, 1 over n squared, that converges. Why? It's a p-series. P is equal to 2, which is bigger than 1. Okay. We know that this series converges. Okay. Same as before. Right. Of course, if we only had, say, n here rather than n squared, series is still going to converge, but then option 1 is the only option, right? We wouldn't have been able to go to option 2, right? Or, you know, if this was maybe like 1/2 to the n in here or something where the geometric series failed, well, again, we could just then rely on the p-series. In this case, we had both options at our disposal. Pick either one. All right, here's another example with comparison. 1 over n minus log n. What do we do with that? Well, let's see. You should probably suspect that this diverges. Why? We know that the harmonic series, 1 over n, we know that that diverges, right? And subtracting something off from n is only going to make the denominator smaller, which is going to make the terms in this series bigger, which should mean it still diverges. And of course, that's the whole point of the comparison test, right? So let's work that through. What do we get? Well, we notice that n has to be bigger than or equal to n minus the natural log of n. Okay. We're working here, let's point out, this is valid for n bigger than or equal to 1, right? If n is less than 1, then the natural log is negative, and this side would actually be bigger. But n is bigger than or equal to 1, so we don't have to worry. Okay, n minus log n. The other thing we should worry about, though, are these terms still positive? Yes, they are. That is still bigger than 0, all right? You can use calculus to check this if you want. It's a pretty straightforward comparison to show that n is always bigger than log n. Okay, this is always true. Simple to set that up and show it. So we know that the terms are positive. We have that comparison. Well, since both of these are positive, we can take reciprocals, inequality diverse, reverses, and we get that 1 over n is less than or equal to 1 over n minus the natural log of n. Okay, very good. And now we can say, since the harmonic series diverges, and you can, however you want to reference this, you can point out, well, it's the harmonic series, and that was our like classic example of a series that diverges despite the fact that the terms go to 0, right? So it's harmonic. Or if you want, it's a p-series with p equal to 1, and it's not bigger than 1, so we know it's going to diverge. And whichever reason you want to give, we know it diverges. We know that this series here, 1 over n minus log of n, that has to also diverge by comparison. And that's it. We're done. All right, before we move on from direct comparison, next topic is going to be the limit comparison test. I want to do one more example with direct comparison, and I want to do this example to try and convince you why the limit comparison test is useful, right? Direct comparison is nice. It gets you the answer really fast if you can set up that inequality. If you can't set it up easily, maybe you want something better. So let's look at these two examples. Now, part A is straightforward. Okay, let's look at the solution for part A. For part A, I can simply say that 1 over n squared plus n is, now of course, I can choose to drop either of these two. They're both positive, right? If I remove either one of them from the sum, I'm going to get a smaller number in the denominator, so a bigger number overall. But I want to keep the one that gives me a convergent series, right? So 1 over n squared, and I know that this series here converges. And again, we know that converges because it's a p-test. P is 2, it's bigger than 1. We know that this series converges as well. And we can give the reason, converges by comparison. Okay, that's not so bad. What about part B? So here's where things get a little bit tricky. The intuition that you want to apply is that for rational functions, large powers dominate, right? And so we should look at this and say, if I ignore the smaller powers, this is effectively a p-series, p is equal to 2, 2 is bigger than 1, I expect it should converge, right? But it's not exactly a p-series, so we have to try and compare to 1, right? The only other difference, you'll notice I started the sum at 2 because 1 minus 1 would give me a 0 in the denominator, which is not good. But as long as n is bigger than or equal to 2, n squared minus n is going to be positive, so we have a positive sequence. We're good to go on that. But we can't do the same sort of direct comparison that we just did, right? If we try it, it's bound to fail, because if I just drop the minus n, right, that subtracting n is making the denominator smaller. If I remove it, the denominator gets bigger, the overall terms get smaller, inequality goes the wrong way. So I can't use it, right? It doesn't work. So what do? Well, you start fiddling around and you just say, like, how can I get this thing to go the right way? So subtracting n, how do we fix it? You can mess around. There are options like maybe you try to complete the square or something like that. I mean, that actually is an option. You could do that. Completing the square might work. We might try to say something like, well, you know what? We know that n is bigger than or equal to 2 in this scenario. If I multiply both sides by n, I know that n squared is bigger than or equal to 2n. Right? I can multiply both sides of an inequality as long as the thing I'm multiplying by is positive. And then I could also multiply by 1/2. So 1/2 n squared would be bigger than or equal to n. Okay? Or in other words, minus n, okay, if I reverse so move this over, minus n will be bigger than or equal to minus 1/2 n squared. So I just swap the two sides. And now I can add n squared to both sides. N squared minus n is bigger than or equal to n squared minus half n squared, which is half n squared. Very good. Okay. So with all that, now I can say that I have my solution, right? So I can say this. I can say, since n squared minus n is bigger than or equal to 1/2 n squared, I know that 1 over n squared minus n is less than or equal to 2 over n squared. And I know that the sum, n going from 2 to infinity, of 2 over n squared converges. Again, p-test, the 2 on top is a constant, doesn't matter, factor it out, it's 1 over n squared. I know that the sum for n squared minus n also converges. And again, it's by comparison, by direct comparison. All right? But that direct comparison was a whole lot harder to set up than this one. Right? You had to come up with this, and you probably don't necessarily come up with that idea on the spot, right? You're in the middle of an exam, maybe you're not going to think about that. That's where the limit comparison test comes in, right? Limit comparison is the test to use with that intuition that highest powers are dominant, right? Limit comparison says, hey, I want to compare this with 1 over n squared. The direct comparison doesn't seem to be working out for me. Maybe there's a simpler way to set this up. We'll see that in the next couple of videos. All right, so now we come to the limit comparison test. All right, so it's still sort of a comparison test. Setup is the same as direct comparison. We have 2 positive sequences. We're looking at convergence of the corresponding series. Okay, and the limit comparison test is essentially trying to set up this idea that if we kind of know in the long run how the 2 sequences compare, right, then sort of smaller differences that might matter for small values of n don't matter so much for larger values of n. They're not so important. We just wanted to look about sort of this sort of long-term comparison. How do they compare once n gets really big? Okay, so if the limit of the ratio is L, right, what that's telling you is that for large values of n, the terms in this sequence are roughly some multiple of the terms in this sequence, right? an is approximately L times bn, where L is some limit, right? So they're kind of the same size, right? Same order of magnitude. They agree, well, not order of magnitude is not the right term, but they're equal up to a constant multiple, right? And we know that as far as convergence of a series goes, constant multiple doesn't matter. If there's a constant multiple, you can pull it out, right? And so these 2 sequences, or these 2 series, either they both converge or they both diverge, because the terms here behave roughly the same as the terms here for long term, right? And convergence really depends on long-term behavior, what happens for large values of n. Okay, so, and then of course it could be that, so L here needs to be positive, right? It can't be 0 and it can't be infinity. So what happens if it is 0 or infinity? Well, if the limit is 0, what is that telling you? That's telling you that these terms here, the bn's, are growing much faster than the an's, right? So these ones are growing faster. So that means that in the long run, the bn's are larger than the an's, okay? So now you're kind of back to direct comparison. The bn's are eventually larger than the an's, otherwise that limit wouldn't be 0. And so you know that if the sum of the bn's converges, well, the bn's are bigger than the an's, so the an's have to converge, right? Essentially, you turn it into direct comparison, okay? On the other hand, if the limit is infinity, well, that means that the ANs are growing much faster than the BNs, right? So the ANs are larger in the long run. And so if you know that this series diverges, this one must as well, right? So the strategy here is always that you want to think of this as like this series here, right? The AN, this is sort of the one that you're given. So you want to think of basically this is like the given series, and this is the one that you're going to compare to, right? That's your comparison series. And so this might be, this might be sort of complicated, right? You're given some complicated series. You want to compare to something that is relatively simple, something where you know what the answer is. You know if it converges or diverges. And you want them to be sort of roughly similar in the sense of long-term behavior. Like if this is some rational expression, well, then you want to look at largest powers of n, right? And set this up based on that. Right? So typically you're setting things up so that you're going to be way back, the very first chapter of calculus, limits. You're doing limits at infinity. You're setting it up so that you're going to do something like a limit of a rational function with equal powers top and bottom to try and get that L. That's the most typical scenario for this, right? But you want to think of the Bn as always your sort of test sequence that you're trying to compare against. So just as a quick example, so that didn't take too long. Let's look at that one that we just left off with, right? We had this sequence, 1 over n squared minus n. Sorry, n started at 2 because we don't want to divide by 0. And you say, okay, I want to decide on convergence of this series by comparison. But we just saw that direct comparison is a pain, really a pain, okay? So we want to compare to, what should we compare to? Well, we look at this, and again, the intuition here, the idea you want to apply is to say, well, look, for large values of n, the highest power is going to dominate, ignore all the rest, right? So it's to throw the rest away, and what you're left with is your comparison. So we want to compare this with the sum n going from 2 to infinity of 1 over n squared. And we know that this is a convergent p-series, right? Okay, so we're going to compare to this convergent p-series, and we simply say, okay, let's look. My an is 1 over n squared minus n. Bn is 1 over n squared. So limit n going to infinity, an over bn. We have the limit n going to infinity of, also dividing by bn, dividing by 1 over n squared is the same as multiplying by n squared. So n squared over n squared minus n. Okay. And that limit is 1, right? Highest degree, top and bottom is equal, right? Power 2 top, power 2 bottom. We look at the coefficients, 1 over 1. We know that limit is 1. Okay? And 1 is bigger than 0. It's less than infinity. So we know that this, going from 2 to infinity, n squared minus n converges by the limit comparison test, right? And if we had the other example, it was n squared plus n, right? So if you had n squared plus n, probably you should do direct comparison. You can still do limit comparison. This exact same thing is going to work if there was a plus here instead of a minus, right? You're still going to get 1 for the limit. But this is slightly more work than direct comparison if it's an easy direct comparison, right? So maybe you want to do direct comparison for plus, but you should probably do limit comparison for minus, because doing a direct comparison for this, we saw that that's actually a fair amount of effort. Limit comparison is relatively straightforward. All right, so here's an example applying the limit comparison test. We wanted to determine the convergence of this series here. We've got 1 over n plus log n, okay? Now, you want to set up a comparison here, and I mean the nicest direct comparison would be to just drop log n, right? You drop log n. But then things get bigger, right? These terms here are smaller than the harmonic series 1 over n. That tells you nothing because harmonic series diverges, and knowing that your terms are less than a divergent series tells you nothing, right? You need these to either be bigger than a divergent series or smaller than a convergent series. And so you need a little bit of intuition. You got to decide off the hop, do you think this converges or diverges? And then choose your sort of comparator, the series you want to compare it to. Choose that wisely, right? It's worth pointing out that if you get 0 for the limit here, and maybe this series diverges, well, then you don't really get anywhere, right? That's a sign that you chose a bad series to compare to, right? Similarly here, if you get infinity and this converges, you get nothing, and it's a sign that you didn't choose very well when you chose that series to compare to, okay? So here, probably you say, okay, I think I'm going to compare this to the harmonic series, and going from 1 to infinity of 1 over n. We know it diverges, but again, these terms are larger than those, right? So the direct comparison doesn't go the right way. That said, we could have done here, if you want to do direct comparison, we might notice this. The natural log of n is always smaller than n. So this is going to be bigger than or equal to, let's make the denominator a little bit bigger, makes this thing smaller, n plus n, which is just 1 over 2n. So if you notice that there is a simple direct comparison, right? This is just half the harmonic series. I pull out the 1/2, harmonic series diverges. Done. But maybe you don't notice that, right? And that's the whole point. So we know that this is the harmonic series. We know it diverges. Okay? And so maybe you don't make that observation. You still want to show that this series diverges. You're pretty sure it diverges. So we're going to use not direct comparison, we're going to do limit comparison. Okay? So an is 1 over n plus log n. Bn is 1 over n. So our limit looks like this. Limit n going from n going to infinity. Again, dividing by 1 over n is like multiplying by n over n plus the natural log of n. Use L'Hopital's rule. Shall we use L'Hopital's rule? Let's use L'Hopital's rule, right? It's infinity over infinity. Derivative of n is 1. I mean, think of it as x if you want. 1 over n. Okay, n's going to infinity. 1 over n is going to go to 0. Again, we get 1 for the limit, so we're in that first case, right? The limit is 1, so either both diverge or both converge. In this case, we know that that one diverges. So we know that this series diverges from 1 to infinity by limit comparison. Okay, and we're done. All right, here's our next example. We want to determine the convergence of this series here, which again has sort of one geometric term and a p-series term. Minus instead of plus. We already dealt with the plus sign example. That was like our very first example that we did, right? We said, hey, we can compare with either the geometric or the p-series. Simple inequality, direct comparison, done. The minus sign makes it a lot harder to set up direct comparisons, so we say, okay, how else can we determine the convergence? Maybe we try for a limit comparison. And now, of course, if you're going to try for a limit comparison, you got to decide what are you going to compare to, the geometric part, the p-series part. Probably safer to compare with the geometric part. Exponential functions grow a lot faster than polynomial functions, so the 3 to the n is going to dominate long term. So we compare to that, right? So solution looks like this. Okay, so we have an is 1 over 3 to the n minus n squared. And we want to compare to bn, and our bn will be 1 over 3 to the n. Okay, and we should probably point out that this is, if we do the corresponding series, n equals 1 to infinity, 1 over 3 to the n is convergent, because it's geometric, right? It's a convergent geometric series. We're good to go. All right, let's take the limit. So the limit, n going to infinity, an over bn. Again, dividing by the reciprocal, we multiply by 3 to the n. 3 to the n minus n squared. Once again, infinity over infinity. If we use L'Hopital's rule twice, right? First time around, you know what, let's just do it. Because it's an exponential, but it's not base e, it's base 3. We get 3 to the n log 3, 3 to the n log 3 minus 2n. Okay, maybe we should put the little h here, L'Hopital's rule. We're going to do L'Hopital's rule one more time. Limit n going to infinity, 3 to the n times log 3 now squared. Don't worry about it, it's a constant. 3 to the n log 3 squared minus 2. Let n go to infinity. The minus 2 doesn't matter, right? We get 1 in the limit. And usual story. Maybe I'll skip writing down the answer because I want to tell you one more thing. But from here we say, okay, the limit is 1, so that's our L. L is bigger than 0, it's less than infinity. We know that this series converges. Now we know that this series converges by limit comparison. Now you might have been wondering, what if you kind of like, I don't know, you messed up. It's not really messed up, but maybe you decided to compare with n squared instead, right? What if you did bn equals 1 over n squared? And you say, hey, that gives me a convergent p series. What would I get then? Well, if I did that, then an over bn, I would get n squared over 3 to the n minus n squared. And we try to take the limit. And again, you can use L'Hopital's rule a couple of times, and you find that this is going to go to 0 as n goes to infinity. Right? We don't get a finite value, we get 0. So did limit comparison, did it fail? Not exactly. Puts us in case 2. Limit is 0. The bn series converges, right? It's a convergent p series. So we know the an's converge as well. Okay? Either way it works. That's the nice thing about limit comparison. There's a fair amount of wiggle room. There's cushion built in, right? It's not quite as sensitive to small mistakes one way or the other. Limit comparison is sort of a blunt instrument. It gets the job done. Okay, so here's our last example using limit comparison. It's the last example for this section on limit and comparison tests. We want to determine the convergence of this series here, right? And now the point that we've tried to drive home with the examples we've done so far is that limit comparison, right, it's sort of a blunt instrument. It's not particularly sensitive to the small details, right? We only really care about sort of largest powers. And so here, if we're thinking about long run behavior, we say what's going to dominate when n is big? Adding 3 is not going to matter. Neither is adding 1. Neither is subtracting n when you're comparing to n squared, right? It's just this root n over n squared, this stuff here. This is the part that matters for large n. Okay? And so we say, let's compare so we want to compare an, which is root n plus 3 over n squared minus n plus 1, to bn, which will be root n over n squared, which is, so that's n to the 1/2 n squared, right? So 2 minus a half is 1 over n to the 3 over 2. Okay? Okay, so let's look. The limit as n goes to infinity, an over bn is going to be the limit. N goes to infinity, so let's put an in there. Root n plus 3, n squared minus n plus 1. And we're dividing by bn, which means multiplying by n to the 3 over 2. Okay? So if we multiply that through, we get the limit n going to infinity of n squared plus 3n to the 3 over 2 divided by n squared minus n plus 1. And that limit is 1, using the typical argument that we just have to look at the largest powers, ratio of the coefficients when those largest powers are equal, right? Okay, so that limit is 1. We're in the first case. And now we say, oh, what do we know about the bn's? This series, n going from 1 to infinity, 1 over, n to the 3 over 2. Does it converge or diverge? It converges, right? It's a p series. P is equal to 3 over 2, which is bigger than 1. We know that our original series, root n plus 3, n squared minus n plus 1, it must also converge using the limit comparison test. Okay, that's it. But again, the point is that you do not want to be handling something like that by direct comparison, right? Limit comparison gives you a straightforward way of setting up a comparison, letting you compare a complicated series with a simple one where we have a known result. And all it's going to cost you is a limit at infinity using techniques that you learned in Calc 1. All right, so our next topic is the ratio test. So the ratio test is stated here as a theorem. Again, the assumption is that we're dealing with a positive sequence, so our series is summing positive terms. We aren't alternating signs at all. And the ratio test gives you a simple thing to consider. It says just look at the ratio of consecutive terms in your sequence, an plus 1 over an. If that limit comes out to a value which is less than 1, you know your sequence converges. If it's bigger than 1, the series diverges. Sorry, I said sequence, meant series. So series converges if L is less than 1, diverges if L is bigger than 1, and if you actually get 1 on the nose, then the ratio test fails, right? So the test tells you nothing if that limit happens to be equal to 1. So one of the things that's kind of important now that we're sort of building up our arsenal of tests, right? We have geometric series now, we have p-series, telescoping series. I mean, there's not really a test there, you just have to recognize that it's telescoping. We have the integral test, we have comparison test, limit comparison, now ratio, soon root, right? Solving problems involving sequences and series is all about choosing the right tool for the job. And it's about doing enough problems that you're able to recognize what the right tool is going to be, okay? So, for example, the ratio test is not the right tool for a p-series, right? If you think about a p-series, right? If my an is 1 over n to the p, right? And if I was looking at, well, what do I get for an plus 1 over an? Well, I'm going to get n over n plus 1 to the p after a bit of simplifying, right? And that's going to go to 1 in the limit, right? So the ratio test is useless for p-series, but that's okay because we already know how to handle p-series, right? We just have to look at that value of p. Is it bigger than 1 or is it less than 1, right? So the ratio test is not helpful for p-series, but it is helpful for a lot of other series. In particular, the ratio test definitely takes care of geometric series, right? Think about a geometric series. If an looks like r to the n, right? Well, then an plus 1 over an is going to be r to the n plus 1 over r to the n, which is r. And as we already know, geometric series converges precisely, for positive r, converges precisely when r is less than 1. Okay? We can see that again with the ratio test. In fact, the way you actually understand why the ratio test works, the way you would prove it, is using something that is sort of based on the geometric series test. It's realizing that, okay, what are we really saying when we say that the limit as n goes to infinity of an plus 1 over an is equal to L? Well, this sort of means that, an plus 1 is approximately an times L for large n, right? And if you think about, well, okay, so this is not a proof by any means, but just think of it this way. So an plus 1 is just L times an, right? And then an plus 2 would be L times an plus 1 would be L times an. And you can sort of, get from here to say, well, that means that, an plus k is like an times L to the k, right? And so then you sort of think about what happens as k gets really large, and you say, well, this is more or less behaving like a geometric series, right? It's not exactly a geometric series because, this is only an approximation. It's not exact. But with the definition of the limit, right, if you bring in, the epsilon definition of the limit, we can say for a large enough n, we can make the difference between this ratio and L less than epsilon. We can work out what that means, and we can make this precise, right? So this is one way to think about why the ratio test works. It's essentially taking much more general series and, in a sense, comparing them to a geometric series, right? But using the machinery of a limit to set up that comparison. Okay? So that's one way to understand why it works. Certainly not a proof, but it gives you some idea of the concept. With that under our belts, we'll move on and we'll look at some examples. All right, so here's our first example with the ratio test. 3 series, 1, 2, 3. I put 3 over here, short on space. We want to see if we can use the ratio test to determine convergence of these series. Now, the ratio test tends to work really well for things like powers and factorials, right? Exponentials. We mentioned that the ratio test is sort of closely related to geometric series. So when you see exponential functions, you expect that the ratio test is probably going to be good. For factorials, the reason why the ratio test works really well for factorials is, you might recall that the factorial can be defined sort of recursively, right? N plus 1 factorial can be written as n plus 1 times n factorial. Right? That observation frequently comes in handy because in this case we would say that our an, right, an is 2 to the n over n factorial. And so we want to set up this ratio, an plus 1 over an. So that's going to look like 2 to the n plus 1 over n plus 1 factorial. Divide by an, we just multiply by the reciprocal, okay? N factorial over 2 to the n, right? And now we can see that there's some cancellation that goes on, right? 2 to the n plus 1, of course, we can, might as well, why not, mention that one too, though I think everyone knows this. 2 to the n plus 1, we can always write as 2 times 2 to the n, right? Laws of exponents, n plus 1, so 2 to the n times 2 to the 1. There we go. And so we see that actually quite a bit cancels here. 2 to the n is going to cancel with all but one of those 2's. The n factorial cancels with, well, the factorial, if you like, right? This n plus 1 factorial is n plus 1 times n plus n factorial. Cancel the factorials. And we see that the limit as n goes to infinity of an plus 1 over an, well, it turns out once you simplify, that's just the limit of 2 over n plus 1. And that limit is 0. 0 is definitely less than 1. And so our conclusion here is that the series converges. Okay. So far, so good. Moving on to the next one. Now, for this next one, there are ways to answer this without maybe even applying a test, depending on how comfortable you are with the sort of long-term behavior of various different types of functions, right? One of the things that you might have encountered if you've been playing around with these things is that factorials grow much faster than exponential functions, right? Because 2 to the n, every time you increase n by 1, you're multiplying by 2 up here, but down here you're multiplying by 1 larger, right? First you're multiplying by 2 over 2, then 2 over 3, then 2 over 4, then 2 over 5, right? So this is getting bigger on the bottom, right? Exponential functions, in turn, they grow much faster than power functions and power polynomials in general, right? So we expect that actually here the numerator is growing faster than the denominator, and you could just apply this sort of basic test for divergence, right? You could say, well, look at an here is 3 to the n over n cubed. And you could say, hey, look, the limit as this, the limit of an as n goes to infinity, the limit of this thing, it's actually infinite, because it's infinity over infinity, but use L'Hopital's rule 3 times. You're just left with 6 on the bottom. You'll still have 3 to the n on top. It's going to go to infinity, right? So this series here fails that most basic test for divergence, right? Which says that the only, if the terms in your sequence that you're summing, right? If the ANs, if they don't go to 0, you know that your series diverges. So this is enough of an observation to point out that the series has to diverge, because it goes to infinity. Of course, you could also, we're supposed to be practicing the ratio test, right? So we could also see this from the ratio test. If we look at, well, what is an plus 1 over an? So this is my an here. And so if I put n plus 1 in there, I get 3 to the n plus 1, n plus 1 cubed, times, so 1 over an will be n cubed over 3 to the n. Okay, so that's going to give me 3 times n cubed over n plus 1 cubed. And in the limit, that's going to go to 1. 1 times 3 goes to 3. 3 is bigger than 1, so ratio test says it diverges, right? Okay, so we can do that. What about this one here? Now this is very similar to the p-series we talked about in the last video. We said ratio test is useless for this, and you can go ahead and you can check. The ratio test is useless. If you try to apply the ratio test, you're going to get a rational function, and it's going to have the same power top and bottom. It's going to be n squared. The limit is going to be 1. The ratio test fails. But we don't need the ratio test for this. We know that this converges by comparison, right? It converges by comparison. With the p-series 1 over n squared, because 1 over n squared plus 1 is slightly smaller than 1 over n squared, right? So the ratio test is not always the right tool for the job. Even here, even something like this where it really looks like, it's the right sort of, ratio test loves power function, or loves not power functions, but exponential functions. It's the sort of form that works for a ratio test. And yes, you can use ratio tests, but maybe you don't need to, right? As you move through tests of sort of higher and higher degrees of sophistication, sometimes you forget that you can come back to these very simple rules that we started out with. They can also do the job for you. All right, so here's a more challenging example. We've got a lot of factorials in there. Ratio test is the right tool for the job when you see factorials. Frequently is, at least. But I mean, n factorial, we've got the square of n factorial on the top. On the bottom, now be careful, that's not just twice n factorial, right? If it was just 2 times n factorial, we'd cancel, we'd simplify, piece of cake. No, this means we double n and then we take the factorial, right? So 2n factorial is way, way, way bigger than n factorial, right? Is it bigger than n factorial squared? Yeah, of course, because here you multiply by the first n integers, and then you multiply by the first n integers again. Down here, you multiply by the first n integers, and then you multiply by the next n integers. It's a lot bigger. Okay? So the denominator is definitely larger than the numerator. Seems like maybe it's going to work out for us, but let's apply the ratio test and be sure. Okay, so let's see. an, in this case, is n factorial, 2n factorial. And so let's look. What do we get when we do an plus 1 over an? So we have n plus 1 factorial, n plus 1 factorial over 2. So do it this way. 2 times n plus 1 factorial. That's going to be 2n plus 2 factorial on the bottom, right? Okay. Multiply by 1 over an, so we flip this thing over. 2n factorial, n factorial, n factorial. Okay? So remember now that n plus 1 factorial we can write as n plus 1 times n factorial. We do that twice, so n plus 1 squared, n factorial squared. On the bottom, this is 2n plus 2, so it's 2n plus 2 times 2n plus 1 times 2n factorial. Okay? Then we have 2n factorial, n factorial squared, if we want to write it like that. And now we look for cancellations, and there are a lot of them. Those cancel, that cancels, okay? And we're just left with n plus 1 squared over 2n plus 2 times 2n plus 1. You can probably see how that's going to go, but maybe just to make things crystal clear, let's multiply these things out. Okay, 4n squared plus 2n plus 4n, 6n plus 2. Okay, so what's the limit? The limit, as n goes to infinity, of an plus 1 over an, well, it's 1 over 4. All right, it's a rational function. Top degree is n squared, top and bottom. And 1 over 4 is less than 1. And that means that the series converges by the ratio test. There we go. All right, so next up is the root test. Root test looks an awful lot like the ratio test. In fact, all I had to do was come through and change a few pieces here, right? So in the root test, it's called the root test because you look at the nth root of an, right, as n goes to infinity. So both the degree of the root goes up as n increases, right? So another way to write that, usually more convenient, is to write that as an to the power 1 over n, right? So we're looking at fractional powers with increasingly large denominator, okay? And we're letting n go to infinity here. Now, it looks a lot like the ratio test, and with good reason. This is yet another variation on the theme of geometric series, right? Notice that if an is r to the n, well then an to the 1 over n is r to the n to the 1 over n, which is just r, right? And we know that a geometric series is going to converge for r less than 1. It's going to diverge for r bigger than 1. Of course, if it's a geometric series on the nose, we also know it diverges for r equal to 1. But it's not exactly a geometric series here, so we can't really say anything if if this limit is equal to 1, right? So the idea here is that, well, if an to the 1 over n, right? If n is large, sufficiently large, right? An to the 1 over n is approximately equal to the limit, L, whatever it happens to be. And that suggests that an is something, it goes something like L to the n. So it really is, again, trying to take whatever series you have and approximate it by a geometric series, and then use what we know about geometric series to decide on convergence of the limit. That's the strategy here. Okay? And again, it's not on the nose, it's only approximate, but it gives you an idea of what's going on. One reminder, for positive constants, if you think about taking roots of constants, for numbers that are between 0 and 1, if you take the root of a number between 0 and 1, it actually gets a little bit bigger, right? Like square root of a quarter is a half. If you take the square root of a number that's bigger than 1, it gets smaller. So for a positive constant, if you take that constant to the power 1 over n and ask where it goes to 1 as n goes to infinity. That's often a useful observation to make. Of course, you can show that using calculus if you like, but we'll just make that as an observation in case it comes up in some of the following examples. All right, so we'll end this section by looking at a few examples that apply the root test to determine convergence. Now, one of the things you'll probably find as you're working through problems is that you don't use the root test nearly as often as you use the ratio test, right? 19 times out of 20, you probably go for the ratio test over the root test. But there are scenarios where the root test is much more effective. Here's one, I think, where it's probably clear that it's easy to use the root test because an is 3n plus 1 over 5n minus 2 to the power of n. And if we want to now take that and raise it to the power 1 over n, right? Well, those two exponents, they cancel each other out, right? Nth power, nth root, those cancel. We just get 3n plus 1 over 5n minus 2. Well, that means that the limit as n goes to infinity of an to the 1 over n, well, this is rational, same power top and bottom. we look at the coefficients, the limit is 3 over 5. 3 over 5 is less than 1. And that means the series converges. Okay, that works out for us. Now, you could probably also do this you could try it using the ratio test. I think you would find that ratio test will also work for you. Root test just happens to be cleaner in this particular case. Okay, if we look at the next one, an, we have n to the 4th over log n to the nth power. So again, we're going to raise that to the power 1 over n. Okay, and what we get is we get n to the 1 over n. Let's be careful here. We get n to the 4 over n on top. We get the natural log of n on the bottom. Now, one of the results that actually, I mentioned this before, if you have a constant to the 1 over n, you let n go into infinity, that's typically going to go to 1. Okay? That's kind of clear, right? I mean, if n goes to infinity, 1 over n is going to go to 0. Constant raised to the power of 0 should give you 1. It's actually also true, though, that if you take n to the power 1 over n, that will also go to 1 as n goes to infinity. Okay? And n to the 4 over n will just be, well, n to the 1 over n raised to the 4th power, 1 to the 4th power, still 1. Okay? So if you take the limit of this one as n goes to infinity, so we have n to the 4 over n divided by log n. Well, this limit is going to be 0, okay? Because the top is approaching 1, the bottom goes to infinity, 1 over infinity gives you 0, right? If you want to go into detail on this, you can play around with indeterminate forms, L'Hopital's rule. I mean, the whole thing is not even indeterminate, right? 1 over infinity is not indeterminate. We get 0. The main thing is making sure that you can see that that top is actually going to 1. If this isn't clear to you, remember you can always rewrite, let me just put this as an aside, that you can always say, hey, you know what, n to the 4 over n, I can write as e to the log of n to the 4 over n, but then the 4 over n comes down. You get that, right? And if you let n go to infinity, log n over n goes to 0. E to the 0 is 1. That's where the 1 comes from. Okay. Coming to the last one. Let's try the last one. An to the 1 over n is going to be 2 to the n to the 1 over n divided by n squared to the 1 over n. So we get 2 over n to the 2 over n. And using the same reasoning as here, this is going to go to 1. That's just a 2. That goes to 2. 2 is bigger than 1, right? Probably forgot to mention in this case here, right? Limit is 0. Well, 0 is less than 1. So that second series also converges. The third one diverges, right? We get 2 for the limit. 2 is bigger than 1. Root test says it diverges. And by the way, for that third one, you probably in practice don't use the root test. Test for divergence, the simple test for divergence tells you already that this series has to diverge, because if you take the limit of just the sequence as n goes to infinity, already you get infinity, right? 2 to the n grows a lot faster than n squared. The terms don't go to 0. End of story. You could also do the ratio test. The ratio test would be easy to apply here. But the root test also gets the job done. All right, so the next topic we want to look at is alternating series. So the definition is here. An alternating series is a series of one of the following forms. So we have these ANs are still kind of positive. So you still start with the positive sequence like usual. But you put this sign factor in front, right? So minus 1 to the n, right? That alternates sign. If n is even, this is plus 1. If n is odd, that's minus 1. Swaps back and forth in sign. So this is how you see the terms, right? So this is going to be, this would be like minus a1 plus a2 minus a3 plus a4 and so on, right? So the sign changes. If you want the first term to be positive, then you do minus 1 to the n plus 1, right? So either way, we consider it an alternating series. Whether the first term is positive or negative doesn't matter. What matters is that the sign alternates between positive and negative, okay? Now, the surprising thing is that for alternating series, right, we know that this condition here, on its own, this condition is not sufficient for convergence, right? We've seen this. We've seen that the series, sum of n going from 1 to infinity, 1 over n, this diverges. All right, this is the harmonic series, okay? Harmonic series diverges. It's a p series with p is equal to 1. There are other ways to prove it, but this integral test does it, but there are direct proofs as well. That is a divergent series, despite the fact that the terms go to 0, okay? But nonetheless, if we have a sequence where the ANs are positive, right? So this, let's be careful. Ha ha ha. I forgot the minus 1. All right, hope you weren't watching the video and turned it off before we got to that correction. Okay, we need the minus 1 to the n in there. Minus 1 to the n times an. It needs to be an alternating series, right? So the ANs are positive, so that this becomes alternating. For an alternating series, as long as the ANs are positive and they're decreasing, then it turns out it is good enough to have the ANs go to 0, right? So this harmonic series diverges, but the alternating harmonic series, n going from 1 to infinity, minus 1 to the n plus 1 over n, that converges, right? Happens to converge, in fact, to the natural log of 2, if you can believe it, right? So we'll encounter this a number of times, right, where the alternating series will converge, but the corresponding non-alternating series, if you drop the sign factor and you just look at the sum of the ANs without the minus 1 to the n in front, right? Without that minus 1 to the n, that series may very well diverge, but you simply put this alternating sign in there and suddenly the series converges, which is kind of interesting. And the idea is that you sort of, if you're looking at the partial sums, you sort of, you start with, let's say a1 is positive, right? So you start at like, here's 0, right? And you add a1. So you're kind of out here. Here's a1, right? And now you subtract a2. But when you subtract a2, you get to a2 is less than a1. So we don't make it all the way back to here. Maybe we make it to here, right? And there's a1 minus a2. And then we add on a3. So we get a bit bigger, right? a1 minus a2 plus a3, right? I mean, maybe we go even further. But, a3 is less than a2, so we don't make it past where we were before, right? We make it out to there or maybe out to there. And then we subtract, and we get a bit smaller. And so you're moving back and forth, but the amount that you're adding or subtracting is getting smaller every time, right? And so if you look at the partial sums when n is odd, in this scenario here, the partial sums when n is odd, they start big, but they get smaller. So you have a decreasing sequence that's bounded below by 0, right? And if you look at the even terms, you have an increasing sequence that's bounded above, say by a1, right? So you've got two bounded monotone sequences. You know that they have to converge. And the main thing is showing that they converge to the same limit. Once you've established that, you would get this theorem. Okay? So We'll look at a few examples. We'll see how the alternating series test applies. And then we're going to come back to this question of convergence of the alternating series versus the corresponding non-alternating series. This gets us to absolute convergence. So absolute convergence is, well, what happens if you take the absolute value, drop the minus sign? Do you still have convergence or not, right? That's going to be an important question. The other thing that we don't have time to talk about is an interesting thing, but it's beyond the scope of a calculus course. Turns out that in cases where the alternating series converges, but the non-alternating series doesn't, this is referred to as conditional convergence. And it turns out that conditional convergence is sort of it's a fragile thing. It depends on the order in which you write down the terms, which is kind of an odd thing to think about, but it sort of comes to playing around with, if you added a whole bunch of the positive terms and then some of the negative and then a bunch more of the positive and then some of the negative ones, there's a surprising thing. It's an interesting theorem that one can prove. It's a very difficult theorem, but it can be done. Once you have an alternating series, you can rearrange the order in which the terms appear to get any real number you want, which is bizarre, right? For a series with only positive terms, you get a limit, and that limit is unique. There's only one possible value. But for alternating series, just changing the order around gets you different answers. It's bizarre. It's a strange thing. Beyond what we can talk about in a calculus course, but if you go on and you take a course in, let's say, real analysis, you might get to play with some of these ideas. All right. So here are three series. We want to know whether the alternating series test, sometimes abbreviate AST, we want to know if it can be applied. The first one is the one we just talked about. It's the alternating harmonic series, right? The underlying sequence, if we ignore the minus 1 to the n plus 1, is just an is 1 over n. And so let's see. This is positive. It's decreasing. And we also know that the limit as n goes to infinity of an is 0, right? So we check those three boxes, right? And this is the interesting thing about alternating series tests. You are just checking boxes, right? There's hypotheses, there's a conclusion, right? So there are three things in the hypothesis. Sequence is positive, sequence is decreasing, sequence has 0 for the limit. If you can check those three boxes, your sequence converges. Okay? So that's it. We know it converges. As I mentioned later on, we'll see that it converges to natural log of 2, but for now we know at least that it converges. Okay, what about this next one? Well, we've got the appropriate form, right? We've got the minus 1 to the n, log n over n. So an is log n over n. So let's see. We need to check positive. We need to check decreasing. And we need to check the limit. All right, so let's have a look. Is it a positive sequence? Well, okay, log of 1 is 0. So the first term is 0, but after that we're fine. So let's say positive. Sometimes we allow 0 for positive. It's at least non-negative. What about decreasing? If you try the first couple values of n, you might find that it's going up, right? So then you get a little bit worried. You're like, oh, it's not decreasing. It looks like the values are going up. Can't apply the alternating series test. On the other hand, the limit is 0, right? Simple application of L'Hopital's rule will tell you that. It's infinity over infinity as n goes to infinity. Take the derivative at the top, you get 1 over n. Bottom is just 1. That limit goes to 0. Check. But it doesn't seem to be decreasing, so you worry that you can't apply the alternating series test. But let's take a look at, if you take a look at the function, right, you look at f of x. If fx is log x over x, then f prime of x, if we do the quotient rule, we get the derivative of the top, 1 over x times the bottom, x, 1 over x times x is 1, minus top times the derivative of the bottom, just log x, bottom squared. Well, that's going to be less than 0 for log x bigger than 1, which is the same thing as saying that x has to be bigger than, well, e is not an integer, but it'll work for 3, right? So it's decreasing for n bigger than or equal to 3, and that's good enough, right? Nobody cares about the first couple terms, right? If you're deciding on convergence, the first couple terms is not going to change whether or not the series converges. You just drop them off the end, figure out the rest, works out. As long as it's eventually decreasing, you're fine, okay? So that works. But then we come to this last one. We got sine of n over n squared, okay? The absolute value, make sure that things are positive, so we've got that again. Definitely the limit is 0, right? Because this is bounded and n squared is going to go to infinity. But it's not decreasing, okay? The terms are not decreasing because sine of n is going to oscillate between 0 and 1. It's going to take values between 0 and 1, and it's going to keep doing that forever, right? As n goes off to infinity, there are going to be values that are close to 1. There are going to be values that are close to 0, right? So yeah, it's bouncing around on it. It's not strictly decreasing, and there's no way to make it strictly decreasing. So in this case, we're out of luck. Maybe it still converges. In fact, it does. We'll see soon that if the series converges without the minus 1 to the n in there, this will be called absolute convergence. If you can show it converges without that term, then it converges with if you put that term in, okay? So it does converge, and it converges just by comparison with the p series, right? 1 over n squared. So it converges, but you can't establish that convergence using the alternating series test. You need to use a different theorem to show that it converges. So the next result we want to talk about is the approximation theorem for alternating series. The theorem's a bit of a mouthful, but the idea is pretty simple. Okay? The idea is that you can actually approximate an alternating series pretty well by any of its partial sums, right? So remember that to satisfy the hypotheses of the alternating series test, the terms in this sequence, they have to be positive, they have to be decreasing, and they have to go to 0 in the limit, right? So these numbers are getting smaller and smaller, they're getting closer and closer to 0, okay? Because you're alternating in sign as you add them, we talked about in the very first video for this section, we said, well, you know, what happens is, you know, you kind of have, you know, maybe somewhere here is like the actual limit of your sequence, right? And so you kind of put the first term in, and so maybe like 0 is over here, right? So maybe here is 0. And you add A1, and you get to here. And then you subtract A2, right? And so then you subtract off A2, and well, A2 has to be smaller than A1, so it doesn't get you all the way back to 0. Maybe it gets you to there, right? And so maybe we'll kind of think about it like this way. We'll sort of think about the difference from L. So A2 gets you to here, right? There's A1 plus, or A1, sorry, minus A2, right? And then you add on A3. You add A3 onto here. And because A3 is smaller than A2, it's not going to get you all the way back to A1. It's going to get you maybe to here, right? Okay, so here will be A1 minus A2 plus A3. And then you subtract off A4. And A4, well, it can't take you back that far because it's smaller than A3 was. So maybe it gets you to, say, here, right? So then you're kind of over here. And there's a1 minus a2 plus a3 minus a4. And now you add on a5, and it can't take you all the way back to there, so maybe a5 gets you to there, right? And so on. So let's call this, maybe to simplify, that should be now S5, right? The fifth partial sum, right? And then S6 might be here. S7 might be there, right? So you get closer and closer to L at every step, right? And you just jump back and forth over the limit every time. And so it's because of this jumping back and forth, right? You're never straying too far from it's not like you're trying to work your way up to the limit. You're jumping back and forth over the limit. And every time the jumps get smaller, right? So that means the difference between the partial sum that you have here and the limit, right? Well, it's always got to be less than the next term, because then when you add the next term, it takes you to the other side of the limit, right? It takes you past the limit. So the difference between the limit and the partial sum, right? The limit of this, so the actual series, right? The infinite series, the difference between them, it's always less than the next term in the sequence. So that's a really useful result. That means if you want to approximate a series, because calculating the actual sum of an infinite series is in general very difficult, right? I mean, there's lots of them where we don't even know what the value is. But we can figure out what it is approximately, because it's easy to calculate the next term in the sequence, right? If we have a formula for the sequence, we can calculate the next term, figure out how big it is. And what that sort of lets us do is say, hey, this gives us sort of a bound on the error, right? And that means if it's good enough to know the sum of the series accurate to, let's say, 3 decimal places, well, we just have to keep going until these numbers are small enough, right? Once they're less than, 1 over 5,000, then we know we've got the answer accurate to 5 decimal places, right? And in fact, we can always just kind of look at the two partial sums, consecutive partial sums. The limit's always in between them, right? So you just kind of look at consecutive partial sums until the interval between them is small enough, and you know that you've got the error that you want, right? So that's the idea. We'll look at a couple of examples, and then we'll move on. We'll talk about absolute convergence after this. All right. So we're going to introduce a little bit more terminology here. We'll talk about convergent series, and we'll talk about 2 different types of convergence now. Absolute convergence versus conditional convergence. So series converges absolutely if you can take the absolute value of every term in the sequence and the series still converges. Okay? It converges conditionally if the series converges, but once you take the absolute value, it no longer converges, right? So the standard example, of course, is the alternating harmonic series, right? So the alternating harmonic series, minus 1 to the n over n, well, that converges conditionally, right? We know that series converges by the alternating series test, but we also know that if we take the absolute value, right, what happens if you take the absolute value of minus 1 to the n? You just get 1, right? So the absolute value gives you the harmonic series, and we know that the harmonic series diverges. Okay, so that's an example of a conditionally convergent series. Okay? Main results on conditional versus absolute convergence. Well, we have a theorem. And the theorem states, and you can maybe guess based on the definition, that if a series converges absolutely, then it just converges full stop, right? So in other words, if the series with the absolute values converges, then the corresponding series without the absolute value will also converge, right? So absolute convergence is a much stronger condition than simple convergence, right? Any absolutely convergent series will converge, but conditionally convergent series don't necessarily converge absolutely. Right? So this is an important result. This comes in handy in a lot of scenarios. And we also mentioned another thing that comes up, and again, we're not going to address this in a calculus course, but if a series converges absolutely, alternating or otherwise, an absolutely convergent series converges to a unique limit. There's only one possible value. Whereas, as I mentioned, a conditionally convergent series can be rearranged. And so you can talk about different rearrangements of a series, and there's a whole section you could study on rearrangements and what can you do there, and you can go through this proof that you can get any number you want by rearranging a conditionally convergent series. Which seems really bizarre, happens to be true. So next up, what we want to do is we just want to look at a few examples to see if we can apply this definition and tell the difference between convergent and absolutely convergent series. All right, so here are three examples of alternating series. And we want to decide if they converge absolutely or only conditionally or perhaps not at all. Looking at the first one, right? If we look at our terms n plus 3 over n squared plus 2n plus 5, well, we might notice that those are approximately 1 over n for n large, right? Okay, we can do limit comparison, right? Using limit comparison, we know that this is going to diverge if we take the absolute value, right? So without the absolute value, we know that this, if we take the absolute value, taking the absolute value, we know that this diverges, right? And we do a simple limit comparison for that. But it does converge. Terms are positive, they go to 0 in the limit, and they're decreasing. You can check, you can use the derivative, right? We can take the function, look at the derivative, figure out where it's decreasing. It's more work than we can fit on the board here. But you can check that this does satisfy the conditions of the alternating series test. So it is a convergent alternating series. So in this case, we get converges, so this will be conditional convergence. Right? Converges conditionally because this does converge. Alternating series test says that it does, but if you drop the minus 1 to the n, it diverges. Okay? It's essentially the alternating harmonic series with a bit of clutter. Very good. Moving on to this one. Well, here we've got that exponential on the bottom. We expect that's probably going to win out over a polynomial on the top. So we might suspect absolute convergence in this case. And if we look at an to be n squared plus 2n plus 5 over 2 to the n. This looks like something where maybe we'd use ratio test, right? Ratio, possibly root. Root is going to get ugly with that polynomial, though, so let's do ratio, right? an plus 1 over an. We get n plus 1 squared plus 2 times n plus 1 plus 5 over 2 to the n plus 1, multiply by 2 to the n over n squared plus 2n plus 5. Okay, so that's going to be 1/2 times this polynomial, which we can multiply the whole thing out if we care to. I guess n squared 2n 4n plus 1 plus 2 plus 5, something like that. Details don't really matter down here, do they? N squared plus 2n plus 5. Okay, so if we wanted to apply the ratio test, we take the limit of that thing as n goes to infinity. It's going to go to 1/2 as n goes to infinity. And so this one is absolutely convergent by the ratio test. Right? Frequently when we're applying the ratio test, we often use the ratio test as a test for absolute convergence. So if we do have sign factors to deal with, we just take the absolute value when we apply the ratio test. You're going to see that in the next section when we talk about power series. Okay. The last one, well, okay, the last one diverges. We don't have to do any work. Why does it diverge? Look at the terms here. As n goes to infinity, that's going to 3 over 5, right? So the limit doesn't go to 0, right? It fails the test for divergence. If an doesn't go to 0 as n goes to infinity, we know it can't possibly converge, absolutely or otherwise. This one just diverges, full stop. The next topic we want to look at is Taylor polynomials. Now, depending on how your calculus course is sequenced, this might be something that you're looking at in the chapter on derivative applications immediately following differentials, or it might be something that you're seeing in the context of sequences in series, and you've just looked at power series, and we're trying to make our way towards Taylor series. So we'll try to do this so it fits both, and we'll probably take this perspective of we're moving on from the linear approximation, right, the tangent line approximation, and we're trying to improve that approximation, right? And then whether you're thinking of this as an application of derivatives or whether you're thinking about why Taylor series makes sense, in either context, this will work out, all right? So we know that this linear approximation, right, it works well. It works well as long as we stay close to this point, right? So there's some point, C here. And so if we go from C to C plus delta x, then, yeah, there's not much difference between the y values along the curve and the y values along the tangent, but only in some little interval here, right? Once we move out to, say, here, that gap's getting big. Out here, the gap's getting bigger. Once we're out here, the gap is huge, right? And it's a terrible approximation, right? It's only a good approximation on a fairly small interval, right? So if you're interested in improving your approximation, there are two choices that you have. One is to shrink the interval over which you're making that approximation, right? You say, well, look, once delta x hits 0.5, the approximation is not good enough. Let's get down to 0.1. Let's get down to 0.01, right? But maybe you can't reach the values you need to reach by shrinking the interval. Maybe you need to approximate the function out here using values of the function over here, right? So that might not be an option. So if you can't shrink the interval, you look for better ways of approximating, right? So we know that if we have this L of x, right? So this is going to be f of c plus f prime of c times x minus c, and this is the linear approximation, right? So the next thing you might ask is, can we do something like, I don't know, let's call it q for quadratic, right? Could we do something like q of x equals, and I don't know, maybe the coefficients are going to look different, but maybe there's an a0 term, right? a1. We'll work in powers of x minus c. You'll see that's going to be convenient, right? And maybe now we go to a second order term, right? And so we say, okay, is there such a thing as a quadratic approximation? Can we do that? Does that even make sense? Right? So of course, adding on that second order term gives some curvature, right? We know the second derivative is where you start curving away from just being a line. So maybe this quadratic, right? Maybe it does something like this, right? Right? So you get a better approximation for a larger range of x values. That's what we're hoping for, okay? maybe you can go to cubic, right? Maybe you can go to, maybe like there's a c of x, right? So there's like a b0 plus b1 plus b2 b3 times x minus c cubed, right? Maybe there's a cubic. And what's that going to look like, right? So you play around and you try to figure this out. Like, can we make these approximations, and how are they going to look? And maybe the cubic, right? Maybe the cubic does something like, you know, maybe the cubic does something like that, right? And you improve the approximation a little bit more. That's what we're trying to accomplish with Taylor polynomials. That's where we're heading, okay? Is we want to introduce polynomials of higher and higher degree so that we improve on the linear approximation, right? So we're going to keep adding, you know, we'll do linear, then quadratic, then cubic, then maybe degree 4, degree 5, degree 6. We'll keep going until we cover as much of the original graph as we need to and as closely as we need to, right? So the idea is, as we add terms, we hope that two things happen. One is that over the original interval that we had, our approximation is better than what we had before, but also that we can widen the interval and have a reasonable approximation for a wider range of x values, okay? We want those two things to happen. So in the next video, we'll play around with this. We'll talk about, well, how do you decide what these coefficients should be? How do we kind of, you know, get things so that it's a good fit? And once we play around with that, we're going to arrive at the formula for the coefficients in what's called a Taylor polynomial. Then we'll be able to look at some examples. Okay, so in the last video, we introduced this idea that maybe if we start adding some higher degree terms onto our linear approximation, we can improve over that original tangent line approximation, right? We can get some curves that match the original graph better and for a better range of values. So the problem becomes one of determining what these coefficients should be, right? And if you're wondering why I chose powers of x minus c rather than simply powers of x, well, that's because we want to make the comparison at this value x equals c, right? So it's nice to be able to just plug in x equals c, and of course, if you do that, all these terms are going to go away, right? So let's say we want to define q of x. What are some things that we're going to require? Well, the minimum requirement that we should put on this thing is that it should agree with the original function at that point, right? So at c, we should have equality, exact equality. So q of c should equal f of c, right? Makes sense, right? They should touch at that point. Okay, so that means that f of c should be equal to, well, a0, right? Because if I put x equals c in here, I get 0, 0, right? So q of c is just a0, right? So now we know what a0 should be. Okay, what's the next sort of reasonable thing that you might ask? Well, we probably want them to have the same tangent line at that point, right? We want them to have the same slope as they pass through, right? If I had my curve and I was trying to approximate by a quadratic that agreed at that point, but the slopes didn't agree, right? I probably have something that looks like that. That's not going to be a good approximation, right? So the two curves should be tangent to each other at x equals c. Well, how do I guarantee that the curves are tangent to each other? Their first derivatives should be equal. So q prime of c should be equal to f prime of c, right? But what's q prime of c? Well, we can take the derivative. This is a constant term, so it goes away. Q prime of c, well, let's say q prime of x to begin with. Q prime of x is going to be a1 times the derivative of x minus c, which is just 1. So this is just a1, right? Here we can use the power rule plus chain rule. 2 comes down in front. 2 times a2 times x minus c times 1, right? The derivative of the inside is just 1. So that means that q prime of c is, well, again, this is going to go to 0, so q prime of c is just a1, and that's what we want to be f prime of c. Okay. So notice what we have so far, right? This is going to be f of c, f prime of c times x minus c. So far it looks exactly like the linear approximation, but we have this one more term, right? So now we come to, well, how do we deal with that last term? Again, we say, okay, so we want the quadratic to be tangent, right? So, but there's lots of ways that we might set things up so that a quadratic is tangent, right? Maybe we have it kind of come in and it does, I don't know, sort of something like this, right? That doesn't look like a graph of a function, but still. The next thing that you want is you want to say something about the curvature, right? So for example, if we were looking, let's say at a maximum or a minimum, right? I could draw a quadratic like this, right? And it would be tangent. These two curves are tangent to each other. They have the same function value. They have the same first derivative at that point, right? But their second derivatives are way off. They're not even the same sign, right? So the next thing that you probably want is you want to make sure that they kind of curve the same at that point. And we know that curvature is concavity is second derivative. So the second derivative of q should equal the second derivative of f. Okay? And we say, what's q double prime? Well, we just take the derivative here. That's a constant. It goes away, right? The constant term always disappears. Then we have 2a2, well, times 1. Okay? So this, of course, that's a constant, so that's also the value of q prime of c. So q prime of c is 2a2, and we want that to equal f prime of c. And that means that a 2, we have to divide by 2, right? Or sorry, f double prime should be f double prime of c over 2. Okay, so it's not simply just putting the second derivative in there, right? We have to account for the fact that as we take derivatives of power functions, right, the powers come down. So we can put that in. F double prime of c over 2 times x minus c squared. And now you've got yourself a quadratic approximation, right? And if you wanted to do cubic, well, it's going to be the same story, right? The work that we did here, it's going to be exactly the same, right? You follow through the steps because what would happen is that cubic term would be along for the ride, right? If we were doing it here, we'd still have the 3 would come down. We'd have 3b3 x minus c squared. Still goes away when you plug in the x equals c, right? Then you'd come down to here. When you did this derivative, you'd have the 2a2. You'd have a 3 times 2 times b3 times x minus c. So again, it goes away. When you get to the third derivative, what you're going to find is that c triple prime of x, or if you like, I guess I shouldn't have used c, and c, oh well. You're going to get, it's going to be 3 times 2 times b3, okay? And you'd want that to be equal to f triple prime at c. So you work that out and you'd find that, okay, so c, the cubic approximation, should be f of c f prime of c, x minus c, f double prime of c over 2 times x minus c squared, and then f triple prime over 6 times x minus c cubed. Okay, and then you got the cubic approximation. And from here you start thinking, you try to figure out what's the pattern, where is this going to go from here. Once you figure out what the pattern is, you can write down this general formula for what are called Taylor polynomials, and we'll do that in the next video. All right, so now we come to the definition of a Taylor polynomial. Okay? So in the last video, we kind of played around. We started with the linear approximation, and then we asked ourselves, what if we wanted to move to a quadratic approximation? What if we wanted to move to a cubic? What would the coefficients of those polynomials look like? Right? So you try to generalize that pattern, and what you come up with is the definition of a Taylor polynomial. So the notation that's used in the Apex textbooks is just P sub n. Sometimes you'll see additional decorations here in the subscript. You might see P sub n, you might see a comma f to indicate the function f, you might see a comma c to indicate the point c. Most of the time we hope that that's clear from the context and just write simply P sub n. So Pn of x, right, is going to be f of c plus f prime of c times x minus c. There's the linear approximation. Next term, f double prime at c over 2. And I'm going to write that 2 as a 2 factorial. You'll see why. It helps us follow a pattern. X minus c squared. And we keep going all the way down to a degree n term. So we use brackets to indicate derivative, right? So the n in the bracket means nth derivative. Nth derivative at c, divide by n factorial, multiply it by x minus c to the nth power, right? So the last power that you have is the degree n term, right? So if it's degree 0, well, that's just a number. That's not very interesting. The degree 1 Taylor polynomial is the linear approximation. The degree 2 Taylor polynomial is the quadratic approximation, right? And then degree 3 and so on, you can go up to, well, really any degree that you want. Okay? So that's your Taylor polynomial. If you like, you can write this in summation notation as the sum k going from 0 to n of the kth derivative at c divided by k factorial times x minus c to the k, right? And for those of you that are watching this in the context of sequences and series, you've seen power series, and so you can probably guess what's going to happen next. You let this sum go not to n. We're not going to stop at a polynomial. We're going to go all the way to a power series. We're going to let k go from 0 to infinity. And then you have a Taylor series, right? Those of you who are seeing this in Calculus 1, you're going to stop at degree n, right? We haven't talked about sequences and series yet. Okay, so that's the formula for Taylor polynomials, right? That factorial, just as a reminder, right? K factorial is notation for the product of the first k integers, so 1 times 2 and so on up to k, right? So 1 factorial is just 1, 2 factorial, 1 times 2, which is 2, 3 factorial, 1 times 2 times 3, which is 6. We saw that in the last video for the cubic, and so on, right? And these factorials, they grow very fast, right? 4 factorial, 24, not so big. 5 factorial, 120. 6 factorial, 720, right? 7 factorial is like 5,040, right? 8 factorial, now you're into like the 40,000s, right? They grow very big, very fast, okay? To make this formula work, there's a convention, right, that 0 factorial is defined to be 1, right, so that you can write all the terms. There are other reasons why 0 factorial should be 1 other than making the formula work, but at this point in your career, you can tell yourself that's why if you like. And of course, the whole point of this Taylor polynomial is that for k equal to 0, 1, 2, all the way up to n, if you take k derivatives of this polynomial and you plug in c, you are going to get the same result as taking k derivatives of your original function and plugging in c, right? The reason you have these factorials is that as you take derivatives, right, using the power rule, right, the first time you take the derivative, n comes down in front, then an n minus 1, and then an n minus 2, and so on, right, until you've taken n derivatives, and at that point, you've got an n factorial out front that cancels with the n factorial here, leaves you with the nth derivative at c. All right? By that time, all the other terms are lower degrees, so they've all disappeared when you take the derivative, right? And of course, if you've taken fewer than n derivatives, there's still going to be an x minus c left in there. So when you plug in x equals c, you get a 0, and those higher order terms, they go away as well, right? So it works out. So the idea here is that you want the derivatives of your polynomial to match the derivatives of your function, and when you do that, you find that the values of your polynomial agree very well with the values of your function, at least over some interval, right? Eventually they're going to diverge, but over some interval they're going to agree, right? If you are in the context of looking at series, right, we'll see later on that as you add more terms, the approximation gets better, and it gets better over a bigger interval. So if you add infinitely many terms, well, maybe you actually get exact agreement everywhere, right? That's the goal of Taylor series, which you're going to see. One last note is that if you put c equal to 0, you get what are called Maclaurin polynomials, okay? So frequently in a lot of problems you'll be working with Maclaurin polynomials just because they're simpler, right? Instead of working in powers of say x minus 2 or x minus 3 or something like that, you just work in powers of x, right? So Maclaurin polynomials are going to look like, you know, f of 0, f prime of 0 times x, f double prime of 0 over 2 times x squared, and so on, right? So you deal with powers of x, and they're a little bit simpler. Okay, so that's how we define Taylor polynomials. It's time to look at some examples where we try to compute these and see how this example works in practice. All right, let's start with an example here, kind of a standard, relatively simple example, computing Taylor polynomials. And we'll hope that this example illustrates a couple of things. One, how the process works, how you come up with the Taylor polynomial, how you sort of identify patterns and then generalize, right? Degree n, right? If we wanted like degree 100, we're not going to calculate 100 derivatives. We want to figure out what's going on. The other is sort of the reason that we care about Taylor polynomials, sort of, right? And the point is that functions like the exponential function, we tend not to think about this these days because we have calculators and computers that will give us the values of these functions, right? For any x value that we want, for any degree of accuracy that we want. We just get it out of a machine, right? But, well, one, there's the question of how do the machines come up with those values, right? How are they programmed to compute these things? You know, and how did people figure this out before they had calculators and computers, right? Because people have been working with exponential functions for a very long time. And, well, back in the day, instead of calculators, what people had were huge books full of tables of values, telling them, you know, if you wanted to know the value of E at 1.6, you go through the book, you'd look it up on the table, and you would get the value, right? This is what you had to do, right? And how did people make those books? How did they fill them out? How did they calculate them? Well, they didn't have calculators available, right? So they had to do computations that could be done by hand. Polynomial calculations can be done by hand, right? All this involved in computing polynomials is powers, products, and sums, right? Or differences, right? So it's all basic, to compute a polynomial, you need only basic arithmetic, right? And basic arithmetic in principle can be done by hand if you're patient enough, right? So you imagine that maybe you've learned all about the exponential function, you know what its derivatives are and things like that, but somehow you've made it this far in your calculus career without actually ever learning the value of e. Well, let's see how you might come up with it. So, first, we're going to try to compute the general degree n Maclaurin polynomial, right? And so remember, Maclaurin means that we're doing a tailored polynomial with this c value set to 0, right? So f of x is e to the x, right? F prime of x is e to the x. F double prime of x is e to the x. And, well, okay, you get the idea, right? Nothing happens when you take derivatives of the exponential function. Okay? So f of 0 is 1. F prime of 0 is 1. F double prime of 0 is 1, right? In fact, all the derivatives of the exponential function are equal to 1 at 0. Okay? So our Maclaurin polynomial, Pn, we know that the definition looks like this. F of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared. You know what, let's go to f triple prime for good measure. Why not? F triple prime at 0 over 3 factorial times x cubed, and so on, down to that last derivative over n factorial times x to the n. But now we know all of these derivatives are just 1, so what we get is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on, down to x to the n over n factorial, right? Which is a fairly nice, simple pattern. Easy enough to follow, right? If you want, you could use summation notation, right? And write this as x to the k over k factorial. Those of you who are looking at sequences in series, let n go to infinity here, and what you will have is actually a series representation for the exponential function. And what we're going to see is that's actually valid for all real numbers. So replace that n by infinity, and this is e to the x, exactly equal to e to the x. But if you truncate, if you stop at some point, you only have an approximation of e to the x, right? So the idea is the more terms you add, the better the approximation gets, right? And the closer you stay to 0, the better your approximation will be, okay? So how do we approximate e? Well, what is e? E is f of 1, okay? Now it says use P5, okay? So how is that going to work? So what that means is we want to say that e is f of 1, and the whole point of these Taylor polynomials is they're supposed to approximate the original function. So f of 1 should be approximately P5 of 1, right? And this approximation should, in theory, be better than the linear approximation. Okay, so what's P5 at 1? Well, we go up to degree 5, we set x equal to 1. So that's a 1, that's a 1, that's a 1. The next, so we have 1 plus a half plus 1 over 3 factorial plus 1 over 4 factorial plus 1 over 5 factorial. If you want to work those out, you get up to there. Okay. And if you want to go a little bit further, you can get everything all over a common denominator. 120 plus 60 plus 20 plus 5 plus 1 over 120. Okay. So 180, 200, 206. Is that right? Probably did something wrong. Good chance I did something wrong. But, so we get something like this, right? Yeah. Okay. And then we say, okay, what is that approximately? Here's where I think this is wrong. 'Cause I think that's less than 2, right? And what we should be getting here is 2 point, so the decimal value should be 2.71667, something like that. Which is why I think I made a mistake. Ignore this part. I've done something wrong there. That part's fine. Okay, so we get this value, 2.7 something, which is pretty good. The calculator value, if you ask the calculator to give you E up to four or 5 decimal places, what you're going to get is, and again, it's only approximate because it goes on forever, but you get like 2.71818, I think is how E starts. Okay, so this approximation is pretty good, right? First 2 decimal places are accurate. We're off by 2 in the 3rd decimal place, and if we added more terms, well, our approximation would keep getting better and better. Oh, I know what's wrong. I fixed it. What did I miss? 1 plus 1. I'm not wrong. I just have to add in a term. So that's not 206, it's 326. Divide by 120, and yeah, that gives you that 2.7. Okay, so as a means of approximation, it's pretty good. What we still have to do is we have to figure out whether we can get some idea of quantifying this approximation. Do we know ahead of time, if we don't know that value, do I know whether or not that's a good approximation? We need some means of testing, right? That's going to come later. Let's do another example. This time we're going to go with a slightly more complicated function, right? We did the exponential function last time. So maybe a little bit too easy because we don't have to do any work to compute the derivatives. I've done the first 4 derivatives here just to get us started, right? And obviously there's a little bit more work involved than there was for the exponential function. But we might also notice that these derivatives, if we're looking carefully, they follow a bit of a pattern, right? So we look and we see what kind of patterns can we see. Ignoring the first one, let's look down here. We notice that we have positive, negative, right? The signs alternate. And you can kind of see that the signs are going to keep alternating because the minus signs are coming from these exponents coming down from the power rule, right? So every time the exponent comes down, we're going to get another minus sign because the exponent's getting more and more and more negative, right? Also, every time we take a derivative, we're multiplying by the next biggest number, right? So when we get to the 5th derivative, we're going to multiply by minus 4. So the minus sign goes away, and now we have 2 times 3 times 4, which is 4 factorial, right? 3 factorial, 2 factorial, 1 factorial. So this is this kind of idea of you're looking for these patterns, right? And you might have to sit and think about this for a while, but eventually you work out that, okay, once I've done k derivatives, okay, well, I'm going to have an x to the minus k, right? minus 1, minus 2, minus 3, minus 4. And we have that factorial in front. Okay. But it's 1 less than the exponent, right? K minus 1 factorial with a k there, right? It's always 1 less. But there's one thing missing, right? What's missing? I'm missing a sign factor. How do I account for that sign factor? Well, the standard way we do this is we use powers of minus 1, right? An even power of minus 1, we're multiplying by 1 an even number of times, it's going to be positive. Odd number of times, negative, okay? So we say, okay, can we just do minus 1 to the k, multiply by minus 1 k times? Well, we look at this and say that doesn't quite work, right? Because, look, it's positive here when k is odd. It's negative here when k is even, right? And that's going to give me the wrong sign. So I could put another minus sign out front, or we just shift this exponent, either add or subtract 1. Doesn't really matter, but maybe you like this to match that k minus 1 factorial. So we put the k minus 1 out front, okay? And now that means that when we put x equal to 1, okay? Well, let's just do this for now. Put the denominator in soon. We've got minus 1 to the k minus 1 times k minus 1 factorial times 1 to the minus k. And of course, 1 to any power is just 1. So what we have here is just minus 1 to the k minus 1 times k minus 1 factorial. Okay, but we know that when we set up our Taylor polynomial, we're going to divide by k factorial, right? So if we do k derivatives, evaluate at 1, divide by k factorial, we've got minus 1 to the k minus 1 factorial over k factorial. Okay, now that simplifies, right? Think about what you've got there. K minus 1 factorial over k factorial. This is 1 times 2 times 3, and so on up to k minus 1. On the bottom is 1 times 2 times 3, and so on up to k minus 1, and then times k, right? So pretty much everything cancels, right? The 2's cancel, the 3's cancel, the 4's cancel. The k minus 1's cancel. All you're left with here is 1 over k. So what we get is minus 1 to the k minus 1 over k, right? And of course, you could also, if you didn't see that, you can do it by plugging in x equals 1, look at the pattern for the derivatives evaluated at 1, and then go from there. Okay, so that means that our degree n Taylor polynomial is going to look like this. Now remember that because we're doing this at 1, we're not going to expand in powers of x like we did for the Maclaurin polynomial. We're going to expand in powers of x minus 1. Okay, so f of 1, what's f? F of 1 is 0, right? Log of 1 is 0. So we start with 0 plus f prime is 1 times x minus 1. F double prime minus 1 times x minus 1 squared, right? Then plus 1 half there, right? Minus 1 from here, but then we had to divide by the 2 factorial, so minus 1 over 2, right? And then 1/3, right? Because we have that 2 factorial over 3 factorial leaves me with the 1/3, x minus 1 cubed, and so on, right? Minus 1 to the k minus 1 over k times x minus 1 to the k. There's your degree n Taylor polynomial. Okay, so now P6 in particular, right? If I wanted to approximate the natural log of 1.5, right, I would say, okay, so P6 at 1.5 is going to be, well, it's going to be 1 times, so 1.5 minus 1 is a half, minus a half, times a half squared, plus a third, times a half cubed, minus a quarter, times a half to the fourth, plus a fifth, times a half to the fifth, minus a sixth, times a half to the sixth. Okay, now, if you actually work that fraction out and you simplify, you get it over a common denominator, what you get is 259 over 640, or approximately, what is it going to be? I wrote it down over there, 0.4047. And if you compare the actual value for the natural log of 1.5, if you look it up using your calculator, you're going to get 0.4055. Not bad. Accurate to 2 decimal places. We're only off by 1 in the 3rd decimal place. Seems okay. All right. Now, if you go ahead and you calculate P6 at 2, well, then those powers of 1/2, they disappear, right? You're just going to have 1. It's just going to be 1, because we're going to do powers of 1, right? 2 minus 1 just gives me 1. So we get that. Okay. And so this works out to 37 over 60, or approximately 0.6167. Okay. And you might hope that, hey, we're gonna get this great approximation again. But this time, well, the best we do is the first decimal place, okay? The actual value, 6931. Actually, I guess if you round, you don't even have the first decimal place, right? So that's not very good, right? So again, we see that even once you go to like a higher degree polynomial, it might still happen that as your delta x grows, right, as the change in x grows, the error in using these to approximate, it's going to grow with the size of delta x. And depending on the function, it might grow faster or slower. For the exponential function, it's actually not that bad. As you add more and more terms, your approximation gets pretty good pretty fast. The natural log, it turns out, and we'll see this if we look at some other sort of analysis techniques. The natural log takes a really long time to give you a good approximation once you go out to 2 or further out. Even if we went to like 100 terms, we still wouldn't be all that satisfied with our approximation. So things really depend on the function for these tailored polynomial approximations. In this next example, we're just going to compute a couple of Maclaurin polynomials. The point of this example is to illustrate something that's going to be useful for you if you are going to use a lot of Taylor polynomials, and especially if you're doing Taylor series. One of the things that comes up is you need ways to kind of do these things efficiently, right? You can't be sitting there all day taking derivative after derivative after derivative until you spot a pattern, right? These things, they tend to get pretty messy. And so far, we've only looked at relatively simple functions, right? Once the functions get more complicated, maybe the pattern doesn't emerge right away, and maybe the derivatives get really messy really fast. Are there other techniques that you can use? Turns out, yes. You're going to see some of those once you learn how to, manipulate series, taking derivatives and antiderivatives of series. There are some tricks that you can do there, right? If you're seeing this in Calc 1, you don't have those tricks up your sleeves, but there's still some basic things that you can notice if you start playing around with some of these examples, like this one here. So for part A, well, we don't know what's going on with the sine function, so we just start taking derivatives and we see what happens, right? So f of x is sine. F prime of x is cos. F double prime is negative sine. The third derivative is negative cosine. And once we get to the fourth derivative, right, we're back where we started, right? So not as simple as the exponential function, but there's still a pattern, right? Cycle repeats every 4 derivatives, right? So once you know how to do, up to P3, you kind of have some idea of how it's going to go from there, right? So we start computing. F of 0 is 0. F prime of 0, cos of 0 is 1. Okay. F double prime of 0 is 0 again. F triple prime of 0 is minus 1. Okay, and from there the pattern is going to repeat, right? So the coefficients are always going to go 0, 1, 0, minus 1, 0, 1, 0, minus 1. So, in fact, if we wanted to, we could say, hey, let's do the degree n Maclaurin polynomial, right? And it's going to look like, well, maybe we say something like 2n plus 1, right? Because the even degree terms don't show up. The coefficient is 0. So what we're going to get is something that looks like x, right? 1 times x minus, so there's no x squared term. So the next term is going to be x cubed over 3 factorial. There's no degree 4 term, right? So the next one is x to the 5, right? So the next derivative is going to be cosine again, which is derivative is 1 over 5 factorial. So you have x to the 5 over 5 factorial, right? And if we wanted degree 5, we're done. Otherwise, go on to 7, and why not? There's 7 factorial. And what does this look like, at the end? So if we think of this in terms of n, this is 2 times 0 plus 1, degree 1. 2 times 1 plus 1. 2 times 2 plus 1. 2 times 3 plus 1, right? So in general, we get x to the 2 times n plus 1 over 2n plus 1 factorial. And what about the signs? Plus signs for 0, 2, next would be 4, and so on. Minus signs for 1, 3, next would be 5. So plus signs when n is even, minus signs when n is odd. So we should have a minus 1 to the n out front. Okay. Well, that's not so bad. Now, degree 10 Maclaurin polynomial for sine of x squared, right? So this gets a little bit trickier because now we've got chain rule with the derivatives, and I need 10 of them, right? And of course, the point of this exercise is for us to realize at the end that we didn't have to do this, but you got to do it once before you realize that. Okay, so 2x cos x squared, right? Second derivative. Okay, product rule now. 2 cos x squared, right? And then minus, so we've got to do 4x squared sine x squared, right? Derivative of cos becomes negative sine x squared on the inside, multiply by the derivative, 2x times the 2x that's already there, right? Okay, and by now you're probably getting concerned that I said I wanted to go all the way to 10 derivatives. Let's do a couple more. Okay, derivative of cos is negative sine, right? 2x is going to come out. Minus 4x sine x squared, okay? Minus 8x sine x squared. So I guess let's just combine. Let's try to speed things up here. 12x And then 4x squared times the derivative of sine cos times another 2x, 8x cubed cos x squared. Okay. Fourth derivative. We're going to get minus 12 sine of x squared. Okay. Minus 12x cos, so minus 24x squared, and another 24, so actually 48x squared cos x squared. Okay. And then derivative of cos is negative sine minus becomes plus 16x to the 4. You tired of this yet? I'm tired of this. Should we keep going? Maybe one more. I don't know if I even want to do one more. Let's do two more. Okay. Minus 12. Derivative sign is cos with a 2x, so minus 24x cos x squared. Plus, okay, a whole bunch of other stuff that I'm not going to do, all right? But it's all going to have x's in it. And x is going to be set to 0, right? We're doing Maclaurin. I just want to point out that the next one, G6, is going to have minus 24 cos x squared in it, and then some other stuff. Okay? So g of 0 is 0. G prime of 0 is 0. G double prime of 0, I get something. I get 2. G triple prime is 0. Fourth derivative, 0. Fifth derivative, 0. The sixth derivative is minus 24. Okay? Which happens to be minus 4 factorial. Not that you were keeping score. Okay, I'll tell you what's going to happen next. The seventh derivative and the eighth derivative and the ninth derivatives, if you cared to keep going, they're all going to be 0. The 10th derivative, it won't be 0, okay? The 10th derivative, well, it's going to give us a number. We got to figure it out. But we're not going to go all that way. Let me just tell you what happens, because this is already kind of, we're pushing 10 minutes here. What we're going to get for my P5 and X, okay, it's going to be, so the first non-zero thing is here, 2. So 2 over 2 factorial, those cancel, right? 2 over 2 factorial times x squared, I get x squared. The next one is here at 6, minus 4 factorial over 6 factorial, okay, times x to the 6th. Now the next term I'm going to get is going to be, so we said it, there's going to be an x to the 10, okay. Should be dividing by 10 factorial, right? But what we're going to find is that in the end, there's only a 5 factorial left over. Okay, so what you actually get for x to the 10 here, it turns out what you're going to get is, it's going to be 10 factorial divided by 5 factorial is the number that's going to come out. Okay, does that work? Yeah. Okay. So the point of this is 4 factorial or 2 factorial. That should simplify, right? Yeah. Let me make sure I got this right. Yeah, it should be. Should just leave with a 6. I might have made some mistakes here. What you should get is you replace x by x squared everywhere. So you get x squared, and then you get 1 over 3 factorial. So this should be a 5 factorial. Times x squared cubed plus 1 over 5 factorial times x squared to the 5th, and so on. And so actually all you have to do is replace x by x squared in the one that you already have, and you get the next one along the way. Okay. I've almost certainly made some calculation errors here. Not surprising given what I'm dealing with, right? It's a bit of a mess. You can sort of see how this might happen. But you should end up with something that looks like that, right? So you can you start playing around, you start learning these tricks. You can plug one thing into another sometimes, doesn't always work out. But you definitely do not want to sit down and calculate 10 derivatives of sine of x squared using the chain rule. That's going to be a terrible mess, right? If you see something like that, you have to guess that probably there was a better way to do it. All right, so we've been looking at tailored polynomials, and we've looked at a number of examples which have suggested that going beyond the linear approximation for your function at a given point C to higher order polynomial approximations gives you better results over a wider range of values, right? So remember that our tailored polynomial, right, looks like f of a plus f prime of a, or sorry, c. We're doing c for our interval, times x minus c. There's the linear approximation, right? Plus these higher order terms, right? Which all come by taking higher and higher order derivatives, evaluating at that point c. We divide by this factorial, and we multiply by the corresponding power of x minus c. Okay? And we've seen that there are some functions like, for example, trigonometric functions where these Taylor polynomials actually approximate very well over a fairly wide range of values. There are other functions like a natural logarithm where these don't work as well as you might like, right? Over a small range of small range of values, not too bad, but there's always a point where you move just a little bit further away and suddenly the approximation is terrible, and it doesn't matter how many terms you add to your tailored polynomial, it doesn't really seem to improve all that much. Okay, so the next step here is once you've established your approximation, you want to know how good your approximation is, right? And keep in mind that you might be doing this in some scenario where you don't necessarily know how to compute the function exactly, right? Because we have graphing calculators and computers and things that give us quite precise values for these functions, we sort of sometimes fail to appreciate why something like Taylor's theorem is useful. Taylor's theorem is useful because you might be in a scenario where you don't actually know how to compute the function precisely, but you can compute tailored polynomials, right? Or some other kind of approximation for your function. And let's say you want to know the value of your function accurate up to, let's say, 6 decimal places, because that's what you're going to display. Well, then you need to be able to figure out how many terms do you need to put in your polynomial to give the value accurate to 6 decimal places at a particular point, right? So at a particular value of x, how big does n have to be before I know I've got 6 decimal places, right? So you might need to solve these problems. Taylor's theorem gives you one means of doing so. Okay, so Taylor's theorem says that as long as you've got enough continuous derivatives, right? So if you want to use a degree n Taylor polynomial, you need this derivative, but you also need the next one. Okay, you need n plus 1 continuous derivatives. As long as you've got enough continuous derivatives, you can write your function as the Taylor polynomial plus a remainder, right? So notice it's equals here. It's not an approximation, it's equals, right? This remainder, right, this should be thought of here as sort of your error term, right? It's telling you, the difference, right? If I move this, if I subtract that over, it's giving you the difference between the original function and the Taylor polynomial, right? So typically what we're interested in here is we're interested in actually the absolute value of this remainder, right? And often at a particular point where we're evaluating things. And so if you're looking at this, you realize that, okay, well, this is just a constant. I don't need to worry about that, right? There's a couple of things here that you have to watch out for. Well, I mean, you have this term, but actually it's not as difficult to deal with as you might think, because for whatever problem you're doing with, you've chosen C in advance, right? You choose the point where you're centering your Taylor polynomial. And now we're trying to decide for a given x, how good is our approximation? So we've chosen our x. The only other wild card here is this t, right? Now, this particular remainder here, this is what's called the Lagrange form of the remainder. It's one of, actually there's like often 3 different forms that you find for this remainder, 3 different remainder formulas. The first one is derived using sort of integration arguments, and it's quite tricky to get to. But once you have that first one, then there are sort of mean value theorem arguments that you can make to arrive at simpler remainder formulas. And so this t here, all we know about t is that it's in this interval that we're working on. Actually, you can say a little bit more. It's between, if you want to narrow it down, it's between x and c. It's somewhere in between those 2 values, right? But typical mean value theorem argument, you know that this number exists, but you don't know what it is, right? All you know that it exists, you know roughly where it's located, but you don't know it exactly. So what you're doing with Taylor's theorem is you're not trying to compute this remainder term exactly, because of course if you could do it exactly, you would know the exact value. That's not the point. The point is to get some measure of how big this thing can get, right? When you're dealing with error, when you're trying to estimate error, right, you want a maximum error. You want an upper bound, right? So you want to be able to say, look, I know that my answer is off by a certain amount, and I know that that amount can't be any bigger than this, right? If it turns out that your error is actually less than what you budgeted for, nobody's going to complain, right? You did better than you advertised, right? You're only going to be in trouble if you advertise that you can do things within a certain error, and then it turns out that you're much higher than that. Then you're going to get yourself in trouble. So typically what you want to do here is you want to look for what is the biggest value that I can get for this function. And we want to look, I guess, at absolute value, right? Absolute value of this derivative. Okay? And we take that absolute value, over this interval I. We divide by n plus 1 factorial, and we multiply by the absolute value of x minus c taken to the n plus first power, right? So there's a few things that you realize with this. One is that if x is fairly close to c, and in particular if the difference between x and c is less than 1, then this is going to get smaller as n gets bigger, right? So just being within 1 of the center of your polynomial is going to give you some control over this remainder, right? So staying within a distance of 1 is going to work. That's why we saw with like the natural logarithm, as long as we did the natural log, we did the Taylor polynomial centered at 1. And between 0 and 2, we did okay. But once we went past 2, once that difference was bigger than 1, we had a really bad estimate. It wasn't good anymore, okay? Because as soon as this difference is bigger than 1, it's going to start growing with n, right? Of course, it's not going to grow as fast as this factorial. So what you're looking for is making sure that overall this thing is getting smaller as n gets bigger. And indeed, it will, right? For pretty much any reasonably behaved function, it's going to get smaller as n gets bigger, right? If you're looking at this in the context of sequences in series, right? Your Taylor series is going to have some radius of convergence, and as long as you stay within that radius, you know that this remainder is going to go to 0 as n goes to infinity. Okay, but if you're just working with polynomials, you're doing polynomial approximations, then you don't care that it's going to eventually go to infinity, right? Like if you have to go out to billions or trillions before you start getting a small enough value, that's not very practical if you're using this to approximate functions, right? You want to know that by the time you get to like n equals 10 or 20, this remainder is small enough, right? You want things to get small relatively quickly. Otherwise, you might be relying on a lot more computational power than you want. Okay? So we're going to see how this formula is used in the next few videos. So we'll do a couple of examples, and then we're going to move on to the next topic. All right, so let's look at an example. We looked at this example earlier, the natural logarithm. We use this degree 6 Taylor polynomial to approximate the values of, so we did this for the natural log of 1.5, and we did it for the natural log of 2. And we found that the approximation was not too bad for 1.5. It wasn't very good at all for the natural log of 2, right? So now we want to kind of look into this remainder and try to understand what's going on. So if we were to calculate the 7th derivative of x, you would find that you get minus 6 factorial over x to the 7. Okay? And if we want to center at 1, right? We probably want to we need an interval that contains the center, and it needs to contain the point that we want to evaluate. So maybe we move like 0.1 either side, right? So maybe we go like 0.9 to 1.6, right? And you could, in effect, if you wanted to, you could probably go with the interval from 1 to 1.5, because this value of t in the remainder formula that you get from Taylor's theorem, generally it's safe to assume that it's somewhere in between these two values, so somewhere between 1 and 1.5. But let's go with 0.9. Let's see where that gets us, right? Let's like I said, if we get an error estimate that's too big, that's all right. That just means we're being a little bit more conservative, right? That's better than trying to come up with an error estimate that's smaller, so you make yourself look good, but then it turns out that maybe you went a bit too small and your error estimate is not actually as accurate as you thought. Okay, so if we use this interval and we want the maximum of the absolute value of the 7th derivative for t in this interval, let's call it I, right? We say, well, I want to make this thing as big as possible for t in this interval. And, well, x is in the denominator, right? So if we have some reciprocal power of x and we want to make this thing big, we should take x as small as possible. That means we should take x to be 0.9. All right? We're taking absolute values, so we lose the minus sign. So we have 6 factorial over 0.9 to the 7. And if you put that through your calculator, you find that this comes out to be about 1506. Okay? All right. If you decided that you wanted to do just t equals 1, right? If we went from 1 to 1.5, you'd get 720, which is 6 factorial, right? So our estimate here is about twice as big, right? You think 0.9 is pretty close to 1, right? But once you raise it to a high enough power, it definitely has an effect. Okay, so we have this maximum, and so now we know that if we're interested in the error, right? Our error is going to be, well, it's going to be given by the remainder at 1.5. And we want the absolute value. So we take the absolute value. And that remainder is going to be less than or equal to. So we have this maximum here, and we've just worked out that the biggest that we can get on the interval we've chosen is 1506. We divide by 7 factorial, and we should actually put in this R6, right? R6. So for n equal to 6, we divide by 7 factorial. Okay, and then x minus c. c is 1, x is 1.5. 1.5 minus 1 gives us 0.5, or 1/2, raised to the 7th power, right? So that 0.5 to the 7th power, that's going to help make sure the error is not too big here, right? Because, you know, that's 1 over 2 to the 7th. That's getting to a reasonably small number. That's 1 over 1,000, right? So we get to here, and again, you can punch this into your calculator. By the way, for when you're doing these error estimates, it's nice to have a decent calculator or even a spreadsheet handy to run the numbers, right? Often, in some situations, you're plugging in various values of n to figure out which one works, and so it's nice to be able to just generate them all and use a spreadsheet, something like that. So if you punch this through, you get that this is something like 0.0023, right? And so what that tells you is that the estimate you get for the natural log of 1.5, right, because the error is less than 5 in this spot, you know that you're good to 2 decimal places, right? Because whatever value you got, you get up to the 2nd decimal place. In the 3rd decimal place, you're off by, plus or minus 0.2. Up to rounding, that's not enough to shift what you've got in the 2nd decimal place. So you're fairly happy with that, right? Now, if we had gone with the natural log of 2 instead, right? So then maybe we're going with 0.9 up to maybe 2.1, something like that. Well, actually, the only thing that changes, the minimum is still going to be down here at 0, or the maximum value is still going to be down here at 0.9, right? So you're still going to have that 1506 over 7 factorial there. But now your x minus c is going to be 2 minus 1. It's 1 to the 7th power, right? And so this doesn't contribute, right? It's just 1 to the 7th. So that's not going to help shrink the remainder. The only thing that really helps shrink the remainder here is that 7 factorial, right? And you can see that this is not going to be very good at all, right? So 7 factorial is what, like, so 7 times 7 is around 5,000, right? So this is, this is around 1,500 over 5,000, something like that, right? So it's less than 1, but it's bigger than 0.1. So it's not as good, right? It's certainly not as good anymore. I guess it's 3,000 over 10,000. So so somewhere around 0.3, right? Which tells you that your answer is, you don't necessarily even have the first decimal place, right? You've got the ones digit okay, but that's about it. So here's where you can see that this is not going to help, right? And roughly, if you kind of play around with this, if you think of where this came from, right? If you go to a higher degree, what you're going to have is the remainder is going to be more or less that that 0.9 factor, if you want, right? You can creep closer to 1 if you want to kind of get it a bit better, but then even if you went with 1, with t equal to 1, your best case is going to be still n factorial over n plus 1 factorial, which is 1 over n plus 1, right? So that tells you that, to get even the first decimal place, you're going to need like 10 terms. To get the second decimal place, you're going to need like 100 terms, right? 3 decimal places, you need like 1,000 terms. So if you're trying to approximate, log of 2, this is probably not how you want to do it. All right, let's look at another example. Now this is one that you probably shouldn't try to do by hand. Chances are you want to have at the very least a scientific calculator with you. Even better would be a spreadsheet. I'll try to explain why as we get there. Okay. So the goal here is we want to approximate the cosine function with a Maclaurin polynomial. And we want to figure out what is the smallest degree that we need if we want to make sure that our approximation has a certain degree of accuracy when we are approximating cosine of 2, right? So we know that our Maclaurin polynomial for cos, okay, if you work through this example, it looks something like this. 1 minus x squared over 2 factorial, x to the 4 over 4 factorial, x to the 6 over 6 factorial, x to the 8th over 8 factorial, x to the 10 over 10 factorial, and so on, up to whatever, you know, depending on the degree, how far you want to go, okay? So that's what the Taylor polynomial for cosine looks like, Maclaurin polynomial. We're centering at 0. We want to figure out how many of these terms do we need to include to get this degree of accuracy, right? So cos of 2, we'd approximate with Pn of 2. So we'd approximate with 1 minus 4 over 2 factorial plus 16 over 4 factorial, right? Minus 64 over 6 factorial, and so on. We want to try and approximate this. So again, we rely on Taylor's theorem. And we say, okay, I know that by Taylor's theorem, I know that the remainder is always going to be less than or equal to this maximum value for the n plus first derivative at some t over n plus 1 factorial, right? And then this is just simply going to be absolute value of x to the n, right? Because we're centering at 0. So x minus c just becomes x. All right, now, one of the things that we know here, right, is we know what these derivatives are. Now, of course, it depends on n. But we know that these derivatives, they cycle, right? We're going to take the first derivative, we get negative sine, then negative cos, then positive sine, then positive cos, and then repeat, right? So every 4 derivatives, it repeats. So we know, well, the absolute value eats that plus or minus, right? So this is either going to be cos t or sine t once you take the absolute value. Okay. And I haven't written down an interval here. I guess we could go with something like, you know, from minus 0.1 up to 2.1, something like that. But it doesn't matter because we know that, what do we know about these trig functions? We know that the absolute value of cos is always less than or equal to 1. And we know that the same thing is true for sine, right? Doesn't matter what t is, these can never be bigger than 1. This is a property of sine and cosine functions. So that means that regardless of the interval that we're working on, this maximum can't be bigger than 1. So the remainder, if we're doing this at 2, has to be less than or equal to 1 over n plus 1 factorial times 2, to the n plus 1. Okay? And now the rest is kind of trial and error, computational work, plugging in values of n until you find the first n that gives you a small enough value, right? We want it to be less than 0.001. This is where a spreadsheet is really great because all you do is you take one column and you label it n. And you have another column that you label, I don't know, rn or error or something, right? And you just fill the values down. In fact, I think if you put 1 and you drag, it will fill the rest in automatically on a decent spreadsheet, right? And then the rn, you say, okay, so what is rn? You can kind of program this into your spreadsheet, right? You say it's going to be 2 to the power of, so if this is in like cell, maybe this is like A2 here, right? So you're like, okay, so it's going to be 2 to the power of A2 divide by, plus 1, right? Because we add 1 to the exponent, divide by like factorial A2 plus 1. And then you just copy it down, right? And when you copy in the spreadsheet, it's going to increment this as you copy it down. And then it's just going to do those calculations for you automatically. So you don't have to do it. It's great, right? But of course, you can do these, right? You can start working them out. So when n is equal to 1, you get 2 squared over 2 factorial, 4 over 2. You get 2. Well, that's definitely not going to work. So you go to n equals 2. 2 cubed over 3 factorial, 8 over 6, 4/3. It's about 1.3-ish. Still too big. You go to n equals 3. 2 to the 4, 16 over 4 factorial, which is 24. That's 3/4. So you're at 0.75, right? And you keep working your way down. You keep doing these. So you go, okay, n equals 4, 32 over 5 factorial, so 32 over 120, and you get to this is about 0.267, right? And then you go to 5, so 5 plus 1 is 6, 64 over 6 factorial, so 64 over 720, and you get something like, I've got the numbers written down over there, I don't remember these. This is now 0.084, getting better, right? So you keep going. For n equals 6.025, right? 6 plus 1, you get 2 to the 7. So we're at like 128. 7 factorial is getting, we're getting there to like 5,040, right? But still, okay? And now, one of the things that you'll notice as you play around with these examples is factorials, they grow much faster than exponentials, right? Because here you're just multiplying by 2 each time. Here, the next thing you multiply is bigger than the previous thing, all right? So you keep going. And the next one you get, you're doing like 256 divided by like 40,000 and something, and you get 0.006. And then you try 8, and you got 512 for your 2 to the 9. And then you're dividing by 9 factorial, which is like 362,000 something. And you get 0.0014. Almost there, but not quite, right? So you say, we got to go to 9. So we go to n equals 9. And for n equals 9, right, you get 2 to the 10 over 10 factorial. Okay? So 2 to the 10 is like, is 1,000. It's 1,024. 10 factorial is, I don't know, it's like 3 million something, right? 3 million and something. And you do get something which is indeed less than 0.01. So you're like, yes, I guess I got to go to degree 9. But that's not quite the end of the story, because hey, here's our polynomial, right? The coefficient of x to the 9 in the Maclaurin polynomial for cos is 0. Okay, so right, I can actually stop at 8 because the degree 9 Maclaurin polynomial is the same as the degree 8 Maclaurin polynomial, right? Because when you go to degree 9, you're adding 0. Nothing changes. So in fact, n equals 8 will do, right? And then maybe you're concerned. You're like, hey, but this number was too big. Like that doesn't make sense. How can we get this much smaller number for n equals 9 than we have here, but they're the same polynomial? Like, shouldn't the error be the same? And of course, the error is the same because remember, we don't know this value precisely. We're always just going for the worst case scenario. What's the biggest that it could be, right? These numbers here are bigger than the actual error, right? So typically, once you get something that's close to the area you're looking for, because you're overestimating, you're probably already good at n equals 8. But sometimes you add one more term just to be safe.